Polymorphic malware, dangers, detection and life cycle. In this session, I am going to talk about how do we uncover the secrets of polymorphic malware. Sophisticated threats that constantly change its code to evade the detection. Much like a spy changes its appearance to avoid the detection of the security controls. First, let's understand what the malware is. As we all know, it is essentially software with a malicious purpose. It means to create a harm, damage the system, or compromise the system, right? So, disrupt, damage, or even gain unauthorized access to the systems. It's as good as the digital equivalent of a burglar, right? With the various types such as viruses and ransomware. Now let's talk about nature of the polymorphic malware. I'll give you an example. Imagine burglar who can change their appearance whenever they want. Polymorphic malware does exactly the same. I mean with its code. It changes itself with each new infection. So typically, polymorphic malware operates with a mutation engine. It's a tool that tweaks its code and ensures that no two infections look the same, though it changes its appearance. Though it changes its appearance, the malicious intent, the payload, remains the same, like a criminal with the same intent but different appearances. So here the mutation engine will shuffle the order of the malware instructions or add random or ineffective code that confuses standard cyber detection tools. So the danger of the polymorphic malware is it constantly changes and makes it's difficult to catch. So traditional antivirus and anti-malware solutions which work like wanted posters with a picture of known criminals. So it fails to recognize this malware because it never looks the same way twice. So detecting polymorphic malware is like trying to find a chameleon in jungle. So it's always blending in, it's a signature, the unique identifier is always changing. And sometimes even it may even play like dead or hide within legitimate processes to avoid the detection. Then what are the modern techniques to catch the chameleon, I mean polymorphic malware? But not all is lost. We have advanced tools and techniques. What are those? Behavioral analysis. It means observe the behavior of the programs, something like watch for suspicious behavior in a crowd. And another technique, heuristic analysis, that look for patterns or characteristics typical of the malware. This is something similar to recognizing the behavior of someone up to no good, even if you have never seen them before. And also another technique, sandboxing, isolating suspect in a controlled environment to see what they do, much like police interrogation. So in the game of digital cat and mouse, the key is to stay vigilant and informed and keep your software updated and layer your defenses and so on. So here, let's look at this diagram which will visualize the life cycle of polymorphic malware. It starts with an infection, then it enters a phase where it changes its code, reshuffling its instructions and adding fluff to alter its appearance. After reconstruction, it emerges with a new form, new binary form, and then it changes its signature and it evades traditional antivirus anti-malware solutions and start the cycle again. So each step here is like a scene in the spy movie, with a malware slipping into new appearance and ready to infiltrate once more. So this is how the polymorphic malware life cycle is. Anyway, in upcoming sessions, I will demonstrate how to analyze polymorphic malware or how to detect polymorphic malware. So that we will discuss in upcoming sessions. Understanding autoencoders, deep dive. In this session, I am going to focus on autoencoders. It's a fascinating tool in the field of artificial intelligence. They are like secret agents. Autoencoders are good at in compressing the information to its most essential form and then reconstruct it back to its original state. Don't worry, so I will explain and I'll give you more examples so that you will have better understanding. So what is an autoencoder? I'll give an example. Imagine you have got a whole album of photos, but your phone is running out of space. You want to keep all your photos? Yes. Then you need to shrink them down so they take up less room. It means either you compress it or optimize such that it can take less space in the phone. So an autoencoder is a type of AI that does just that with that data. Similar form, similar way. It learns how to squash the data down to a smaller size and then expand it back out so that it can keep all the important bits intact. I'll talk about architecture here. The autoencoder has two main parts. One is encoder, other one is decoder. So encoder is like expert packer who can take a suitcase full of clothes and pack them down into tiny bag. That's an example. So that and make sure that most important items are included. Essentially, it'll take the input data, it compress such that it can take up less space. And then decoder. Decoder is something like someone unpacking the tiny bag and trying to trying to put all the clothes back as they were, outfit by outfit. That's a decoder. Autoencoders are trained in a special way. They practice taking the input like a photos, squeeze it to down, like you would have seen that in the input data, there you see that more neurons, but then it compress it, it convert it to the essential form that it is squeezing it down. See here 4 neurons and then 2 neurons, right? So you squeeze it down and keep a most essential form in it. And here, trying to recreate the original as closely as possible. The goal is to make the recreated photo look as much like the original photo as they can. Because initially, it would have squeezed it to and so that it can take very less space, right? Maybe by compressing it or maybe by optimizing it. But here, it recreated and whatever optimized, whatever it is taken out, that, but then it try to create the original photo as they can. Even though they have squeezed it down to a smaller size in between. I hope you understand. I hope you got the point. Let me give you another example. Let us say if you had to describe a movie you saw in just one tweet, then you would pick the most critical parts to mention. Because you cannot write everything in one tweet, right, about the whole movie. But here you can pick the most critical parts to mention. So later, someone should be able to read your tweet and get a good idea of what the movie was about based on the critical parts. That is what it is about. Here the encoded data, that is which is in a latent space where that is a critical parts. Right? So that's what an autoencoder does with the data. I'll talk about some few applications of the autoencoders, data compression, just like a shrinking photos to save space on your phone. That's one application. Other one is anomaly detection. If an autoencoder is trained on a normal transactions and then sees a weird one, it'll be like this doesn't look right. That is what it is helpful for catching the fraud or for anomaly. And also another application is image denoising, where it can clean up the photos, remove all the static and fuzziness to, give us that with a crisp image. So these are the some generic applications, and of course this is most important application of the autoencoder, especially in the metamorphic and polymorphic malwares detections that I am going to talk about in the next sessions. But here for your understanding, I am just talking about the general applications here. So with respect to cybersecurity, I am going to talk about especially using autoencoders in metamorphic and polymorphic malware detections. That I will talk about in the upcoming sessions. Okay, having understood the generic applications here, let us talk about some challenges and considerations here. And one point is autoencoders have to be carefully balanced, because it makes too simple and it won't capture all the details, right? If you make it too simple, it won't capture all the details. That's another problem. And if you make it too complex, and then it just memorizes the data without learning anything useful. So either too simple or too complex is always problematic with the autoencoders. So that's why autoencoders have to be carefully balanced. I'll talk about one real world example here. Take a Netflix. They have tons of data on what movies people watch. And they could use an autoencoder to squeeze all the data down and then use it to figure out what movies to suggest to you next, all based on what it learns about viewers' preferences, isn't it? So that is what actually autoencoder does that. So you can use here Netflix and then suggest what movies and people can watch next based on their viewer preferences, where you can apply, you make use of autoencoders for that. That's the real world example. Let's look at this diagram here. Input data. This is like the full detailed story of what happened on, say, let us say, for example, you have gone for a weekend trip, right? So here the input is, it's like a full detailed story of what happened on your weekend trip. I'm just taking example to make you understand better. So that's why I'm taking out of the context. Here I'm not talking about the cybersecurity here. I'm taking generic example so that we understand better, and then we'll move on to, with respect to cybersecurity context in next sessions. So here input data is like a full detailed story of what happened on your weekend trip. And then we will move on to the encoder, where it summarizes your story into just highlights. That's the encoder it does. Then latent space or code. This is the summary. It's essential points of your trip from the highlights. And decoder, it tries to tell the full story again, just based on the summary, based on the essential points, just from the highlights. And here reconstructed input. This is the retold story. Hopefully it sounds like a lot like the original. It's the original story here. How about reconstruction error? This reconstruction error, it checks if the retold story left out any important parts. Everything is covered over the weekend trip. So the less it misses or it leaves out, the better the autoencoder is doing its job. It means it has captured all the essential parts or important parts from the weekend trip. So the less is better. That's where we say reconstruction error is less. And that's how we can say that autoencoder is doing its good job. So in essence, autoencoders are like the art of storytelling, where you can learn to capture the essence and then retell the tale. So keeping the core message alive. They are a very powerful tool in AI that helps us to tackle the vastness of the data by learning what is truly important. Polymorphic malware detection using autoencoders. In this session, I'm going to talk about using smart technique, that is autoencoders, to detect the polymorphic malware. Let's understand the polymorphic malware. Imagine a criminal who changes their appearance every time they commit a crime. So polymorphic malware is something similar to that. It changes its code every time it infects a new computer or a new system. So it's really hard for the computer security or for the traditional antivirus and anti-malware solutions to catch it. So here, the first things what we should do in order to detect polymorphic malwares, first we need to gather or extract the features. I'll give you an example. The first thing we need to do is like gathering clues at a crime scene, isn't it? So we look at the malware code, polymalware code, its DNA, and find a specific clues or patterns that tells us whether it is up to no good. Here is where autoencoders comes in. Think of an autoencoder as a sketch artist. You give them a bunch of features about someone's face, and these autoencoders draw a picture of that person. So then you compare the picture to the person standing in front of you. If the drawing and the person match, great. If not, something is off. So training an autoencoder is like teaching the sketch artist. At first, their drawings might not be very accurate, but the more you train them with the pictures of people's faces, the better they get it at drawing them accurately. So once trained, if we give the autoencoder a face it's never seen before, like new version of the virus, new version of the malware, it will try to draw it. If the drawing comes out looking nothing like original, the autoencoder tells us that something unusual is going on. It means there is anomaly. This is how we spot the malware trying to sneak in with a new disguise or new appearance with a new code changes. So when we find something unusual, it's like a security alarm goes off. The system sends on an alert, and then the cybersecurity team steps in to take a closer look, just like the police would all after an alarm goes off. Why autoencoder? Because autoencoders are great for this job because they are really good at learning what normal computer code looks like. So when they see autoencoders see the code that trying to hide something, they are quick to spot it. So autoencoders helps us catch these polymorphic malwares by learning what it usually looks like and then look for anything that doesn't fit that pattern. Lab session polymorphic malware detection using autoencoders. So in this lab session, I'm going to demonstrate detection of polymorphic malware using autoencoders. Before we dive deep, let's understand the polymorphic malwares. I'll give you an example here. Imagine you have a magical box that identifies fake currency notes. You feed it a note to that magical box and it tells you whether it is a genuine or counterfeit. So in our scenario here, this magical box is nothing but autoencoders. Autoencoder is a type of neural network that identifies or helps to detect polymorphic malware. You might wonder what is polymorphic malware. As we discussed in previous sessions, polymorphic malware changes its appearance every time it infects new system, and it makes it hard to detect. It might use different encryption, different compression algorithms, but underneath it the behavior and payload remains same, but only the appearance changes every time it infects. So that is why it's hard to detect. So this is where autoencoders would help to detect polymorphic malwares. You might wondering why autoencoders are chosen for polymorphic malware detection. I'll give you, there are several reasons why we have chosen autoencoder for polymorphic malware detection. So let's understand key reasons why autoencoders are suitable for detecting polymorphic malware. There's one reason that anomaly detection. Autoencoders are excel at anomaly detection. It learns to compress and reconstruct the normal data, that means that benign software patterns. Autoencoders identify anomalies or outliers that significantly deviate from these learned normal patterns, especially polymorphic malware ones that differs from common software patterns. So that can be detected as anomalies based on the reconstruction error. So that is why autoencoders are chosen for the polymorphic detection. There is another key reason, that learning high-level features. Autoencoders are good at learning high-level features in an unsupervised manner. This is particularly useful for polymorphic malware detection because it allows the model to capture key characteristics of the software behavior without explicit labeling. So this way it makes to learn or identify underlying patterns or anomalies even if the malware appearance changes. So it detects underlying patterns. So no matter what type of encryption or compression uses or appearance changes, but still it detects and identify underlying patterns or anomalies. That is a key reason why autoencoders are chosen. There is another reason, key reason is that adaptability to new malware variants. Autoencoders adapt to new and unseen variants of the malware. This is crucial, especially in the case of polymorphic malware detection, because polymorphic malware generates numerous variants to evade the detection, to bypass the detection. So autoencoders can generalize from learned representations of benign and known malicious samples and then identify new variants because based on deviation from the norm. Another key reason is it is very effective to evasion techniques, that is bypassing techniques. It's very robust. Polymorphic malware often uses evasion technique so that it can avoid detection, like obfuscating the code, changing the appearance by using different types of encryptions and compressions and so on. So autoencoders focus on reconstructing input data and identify reconstruction anomalies. So that is more robust to evasion techniques when it compared to the that specific signatures or heuristic based methods. And also another good property of the autoencoder is that it is unsupervised nature, and that's where it makes very suitable for the you know polymorphic malware where we do not have a sufficient labeled data, right? It's hard to get that. Autoencoders learns some useful representations
and detect anomalies, right, without the need of larger labeled data set. That is a very good key reason why we considering autoencoder for the polymorphic malware detection. And also it is efficient at scale. It autoencoders efficiently process and analyze large volume of data, right? And it's very makes it suitable for real-time malware detection in extensive networks. And also it compresses the data into lower dimensional representation. It means it can reduce that computational load and storage requirement. So that is why autoencoders is beneficial for deploying detection system at even scale, in large scale. So to summarize, autoencoders are chosen for the polymorphic malware detection due to several key reasons, like you know learning high level features in an unsupervised manner, adapting to new malware variants, and it provides a robustness to evasion technique, and it helps to operate efficiently at scale. So these qualities, these key reasons makes autoencoders is a compelling choice, a very good choice for identifying polymorphic malware. Okay, having understood that why we have considered autoencoder for polymorphic malware detection, we will let us understand this flowchart that helps to detect polymorphic malware using autoencoder model, right? So here library first, because we import necessary tools and generate the sample data, right? So here this data what we create or collect is that show that what how normal and polymorphic malware look like. So that is what the data it is. So generate the data here that includes both normal and polymorphic malware data sets. And then here we convert the data into tensor, and then we define the model, and so that can learn what normal data look like, and autoencoder try to compress the data and then recreate it, and it learns the patterns in this process here, right? Afterwards we teach the our model, autoencoder model, using the examples which we have collected, that improves, and it helps to recognize and recreate those patterns by training it. And we will move on to evaluating model performance on test sets. After training, we test the model with the new examples it has not seen before, to see how well it can guess whether they are normal or malware. And finally, we use the model to predict if a new example is likely to be polymorphic malware based on how well it can recreate the example, right? In case if the model struggle to recreate it accurately, then it might be a malware, since it doesn't fit the pattern of normal data that the model learn, right? Okay, I hope you got the flow chart for detection of the polymorphic malware using autoencoder model. So don't worry if still you have a some doubts, and I will take you through, we walk through that code where we will understand the logic, you know step by step, so that you'll understand better. Okay, I'll move on to the code. Here is a code where we understand that logic in step by step. Okay, let's begin. And we import necessary libraries like a torch and sklearn and numpy. Then afterwards we will move on to generating the sample data, and of course this data is for the demonstration purpose, so I kept it. So here this particular script, it create a random data set of 1000 samples, right? and each with 30 features, right? So, and also it also assigns labels, random labels, either 0 or 1 to these samples. This is something similar to, creating a mock data set, right? For example, like I'll just give you a generic example, like where we create a mock data set of patients, where each patient has a 30 health metrics, and we want to predict if they are sick or healthy, right? Something like that. So here, whether that is particular one based on the 30 features, and we will assign that whether it is a normal software or polymorphic one. So that is how actually we do it. Then after generating the sample data, we will move on to splitting the data into training and test sets. And the training set is, we use it to teach our model, whereas test set is, to evaluate how well our model has learned here, right? So test set size is 20% and training set size is 80%. And after splitting the data sets into training and testing sets, and we'll move on to converting the data PyTorch sensors, because we need to convert the data into format such that we can process with the PyTorch library. So that is why we need to convert even X and Y, even training and testing set data, so that it can be able to process with the PyTorch library here, right? And then we will move on to defining the autoencoder model, and where we will build the autoencoder, right? And as I mentioned, autoencoder is a neural network, and that learns efficient um, patterns or codings of the input data, and it has two parts. One is encoder, other one is decoder. Here encoder compress the input data into a compact form, right? And this is the encoder. And decoder, it reconstructs the original data from this compact form. First we convert input data into compact, and here the decoder, it reconstructs the original data from the compact form, right? So let us say, to make it more simpler, and I'll just give you one example. Like, let us say, think of encoder as a machine that compresses fruit into juice, and the decoder is another machine that try to reconstruct the original fruit from the juice. This is what it is, as simple as that, right? So, and then we will move on to training the model, and here is a forward function that calls encoder and decoder, and then this is where actually the autoencoder model was defined, and then it called, and here is the one loss and as well as that add optimizer, right? And then after defining that loss and optimization functions, and we will move on to training the model. And here the model autoencoder is trained using the training data, and during this training the model try to reconstruct the input data as close as possible, but the original the difference between the original data and the reconstructed data is what we call it as a loss. So here the goal is to minimize this loss over several iterations, that is over 10 epochs, 10 iterations, right? I hope you got the point. So this is why here we try to minimize the loss as much as possible over 10 iterations, right? 10 epochs. And then after training, we evaluate the model performance based on the test set. This is test set. So the reconstruction error, that means difference between the original test data and the data reconstructed by the autoencoder, is calculated for each sample. If the reconstruction error is greater than threshold, classify it as a malware. Right? So this is what actually we calculated. So the rationale is that here the normal data should be reconstructed well by the autoencoder, whereas malware data would have a higher reconstruction error. That is a very deviation from the original data. So that is where it can flagged as a polymorphic malware, right? And this is what it is. If the sample loss greater than threshold, that is predicted as a polymorphic malware. Otherwise, it is predicted as a benign. So if the reconstruction error is above the threshold, it is classified as a malware. Otherwise, it's considered benign. So in essence, it's an autoencoder detects polymorphic malware by looking at how well it can reconstruct input data. So if the reconstruction, it means converting back from the compact to the original data, is significantly different from the original. If the reconstruction error is high, it's a sign that the data might be malware. That's how we can predict it. I hope you understand the logic. If you have any questions with respect to understanding the logic, and then please post me, post Q&A. I'll get back to you. Having understood the logic, we will move on to the demonstration where I will execute this particular script in AWS. So there we will see how, what insights we can get it, after execution of this script. So here is the AWS, and I've chosen that instant type is medium, and AMI name is Deep Learning OSS NVIDIA Driver AMI GPU PyTorch 2.0.1. So this is the image and instance chosen for the running execution of this autoencoder script, and number of ECUs, CPUs 2. Okay, so you can also choose something similar to, but it is all it's up to you. And here is the prompt. I'll just show you the code, the one which we have discussed just now. Okay, so this is the code here, the same code which we have discussed just now, right? The same code which I am going to execute it. Python, let me clear that. Okay, Python 3, it's a version Python 3 3.0, and poly malware. Okay, so this will take, okay, great. So excellent. So the program and the script run successfully. So what is that we can understand what insights we can get from this output is that, so here is a loss, and there are 10 epochs, right, and 10 iterations, and see whether we whether loss has decreased or not. The loss, it measures that how well the model is performing, right? So but here it is decreased very slightly over each epoch from 0.0856 to 0.0850, right? So this means the model is learning, but the loss is very minimal. Loss has come down very minimal. So it suggests that the data doesn't have enough features for the model, or even larger data set is required, or it could be enough features for the model not there. So that's why the loss has not come down much here, right? And that could be the one reason. And also the model might have reached its capacity to learn from this data. So you may have to train with this model with the more larger data sets. That could be the one reason. Or it may not have enough features for the model to improve its predictions, right? So that is what it is. So here the accuracy, model accuracy is shown as a 49%, and which is close to random guessing in this classification, because since the expected accuracy for this random guessing is 50%, isn't it? So So, but what I understand that given that accuracy and then the sample is predicted as a polymorphic malware, it means that model is not effectively distinguished between polymorphic malware and benign software. That's what it tells, right? So, but one point is, despite in spite of the lower accuracy, the model predicted sample as a polymorphic malware, right? So this might be based on the reconstruction error, because where that it could have been that it would have been higher error, so that indicates that sample is likely malware, right? Right. So anyway, so this requires improvement, this particular model. But as far as demonstration is concerned, and here the idea I wanted to show that now how do we detect that polymorphic malwares using autoencoders? Here is the concept which I have demonstrated here. But when it comes to the deployment, you need to train this model sufficient so that it can predict that it can predict very well and it perform very well and unseen the data, right? So but here the model, it doesn't seems to be performing very well on this task of identifying polymorphic malware based on the provided accuracy metric. So that could be the one reason, so which we need to, why we need to improve this model. But as far as understanding demonstration is concerned, and this is what actually we will use these autoencoders to detect that polymorphic malware. So try out with the different features and enhanced feature set and larger data sets, right? So that you can try to train this model and then evaluate the performance of it, right? So if you have any questions with respect to this model or lab session, and please post them in Q&A. I will get back to you, and so that we will have a good discussion on this.
Real-time case study, polymorphic malware. Let's understand the polymorphic malware, that is Dexpot malware. Microsoft research team has done very good analysis on Dexpot malware. So that I will explain. So the reason is why I am going to talk about is, and why I have chosen this particular malware for the discussion, is that this particular malware, polymorphic malware, which is Dexpot, is very good at not leaving any traces, and it changes its appearance every time it infects the machine, and every time it changes its code, right? It makes it really tough and hard for the standard traditional security tools to detect that. And also it hides it. It's very good in hiding it. At the moment security controls, it detects and then it hides it, and it remains dormant, and it hides it in existing benign processes. So let's understand the Dexpot malware infection process. Right? We will begin with the initiation by the installer, and Dexpot malware, we begin with that. This is a harmless installer. This installer is Trojan horse. It is the trick that starts the entire process. It connects to two different web addresses, URL1 and URL2. It's much like a double agent receiving instructions from the two different sources. From these web addresses, the installer fetches Microsoft installer package, that is MSI package. And this package pretends to be a regular software installation file, but it actually the container that smuggles the malware into the computer. This Microsoft installer, it smuggles the malware into the system. So within this MSI package, there is file which is password protected zip file. To access its contents, the malware employs its own version of the unzip utility, bypassing any need for the computer native tools. So this step is like thief expertly picking a lock to get to the valuable inside. So the zip file reveals it's a secret that is loader DLL. It's a type of file that is used by the software to run the code. But this is not just any code. It's the core of the malware malicious intent. Alongside this loader DLL, there is an encoded data file. This file is like a coded message. It hides this particular encoded data hides the malware true plans in a form that is not recognizable, immediately not recognizable. Now the despot starts using trusted system processes, much like spy who impersonates officials to move around unnoticed. So here it uses msiEXE.exe to run the installer, unzip.exe to open the zip file, and run dll32.exe to run the malicious DLL, schedule task schtask.exe to manage the schedule task, and PowerShell.exe to execute advanced script. So despot uses its benign system processes for its purpose. So despot is meticulous. It schedules the task to regularly check on itself and update as needed. And it ensures its mining operation continues uninterrupted. It's like setting up recurring alarm to remind you of an ongoing commitment. And another very good, important thing is it hides within the legitimate processes. These are all the legitimate process of the system. Because what installers come with this, but restore all legitimate process where despot uses legitimate processes for its intended actions. So this is the technique what we call is process hollowing. It employs that technique. It means despot sneaks its malicious code into legitimate processes. This is a sophisticated form of camouflage. It makes the malware action seems like normal computer operations. By hiding malicious code into legitimate processes, it makes it look like normal computer operations. So the ultimate goal of all these steps is to activate cryptocurrency miner and additional monitoring payloads. The miner uses computer resources to generate cryptocurrency, and that turns the infected machine into silent gold mine for the attackers. Throughout this whole process, despot remains vigilant, and it monitors its presence to avoid the detection and restart and any components or any package that stop working. So it's something similar to burglar who sets up motion sensors to alert them if anyone is approaching their hideout. So by understanding the chain of events, we can appreciate the cunning nature of the polymorphic malware like a despot. Despot means DEXPHOT. It's chain of deception and disguise, each step meticulously designed to maintain the malware's stealthy mining operations. That is the beauty of this polymorphic malware. In simple terms, despot is a sneaky malware that uses your computer to make money by mining cryptocurrency without you knowing. It's always changing, but with a smart security system. That's why we need advanced AI and ML based models or based solutions to detect this kind of advanced malwares, that is polymorphic malwares. In this session, I'll be taking a deep dive into the and focus on behavioral analysis of the files or decoding file behaviors so that we can spot malicious and benign patterns. This is something similar to understanding the difference between friend and enemy based on their actions. So let's getting into this. Malicious file behaviors. Let's understand malicious file behaviors here. Network activity. Malicious files often communicate with the outside world. So they can send out sensitive data or reach out to a command and control server, right? It's like much like a burglar phoning home. So network activities. So monitor that it's unusual outbound traffic and scanning local network. So this is the one of the typically malware, perform this network activity. File system activity. This is one of the malicious file behavior is that malicious files can identify, can modify, delete, or even add new files to your systems. So it's like a modifying system files and dropping files, right? So they can drop other malware into your system, acting as a digital Trojan horse. Process activity. This is one of the malicious file behavior. Pulling the strings of other programs without your consent. This is what malware does when it hijacks legitimate processes to mask its activity or perform malicious actions. Right? Process injections, right? And spawn processes. So it can inject process into existing process or it can create new processes, right? This is one of the malicious file behaviors causes that. Registry activity. The registry is the rule book that is used by the computer, by which your computer operates as per the rule book. That's a rule book. Registries means rule book. So malware can rewrite the rules in the registry to suit or to meet its needs. It's much like a burglar tampering with your home security systems. So modifying the registry or creating new registry keys. So modifying the rule book so that the way it wants the system to operate, it can make it by modifying the registry content. Memory activity. Some malwares hides in the computer memory. It's a bit like criminal hiding in a crowd. And it makes it difficult to detect and eliminate. So by exploiting that memory vulnerabilities or by residing that malware in that memory. Evasion techniques. The most cunning malware can defend itself. It might disable your antivirus tool, a solution, or hide from that. And it can even detect virtual environment, and so that it can see what it can do. Something similar to burglar wearing gloves to avoid leaving fingerprints. That's the evasion technique. User data activity. The most insiders malware watches quietly. It records your keystrokes, or it can steal the data, stealing your files, or sending data out. So something similar to spy gathering intelligence. So that's a user data activity. So these are all the malicious file behaviors typically that malware does. So having understood that behaviors or patterns of the malicious files, let's look at the benign files behaviors. What is the behavior of the benign files or normal files? Network activity. Legitimate files also need to talk to the internet, isn't it? For reasons like updates or synchronization and so on. File system activity. Good files will access the files they need to function properly, but they don't move or modify that unrelated files. They are like a guest in our home who doesn't snoop around in personal areas. That's a good files. Process activity. So non-malicious files operate smoothly with other programs. Like this is something similar to team player in a game, right? They don't disrupt the activity of other applications. So they operate smoothly with other programs. That registry activity. Legitimate programs use a registry to save settings and preferences like person keeping a diary. They don't make unauthorized changes, right? Memory activity. Good files use memory to operate but don't hide or linger unnecessarily. Think of it as someone using a shared space respectfully. That's a memory activity. User data activity. Users only interact with your personal data when you have given explicit instructions. Right? So this is what the user data activity. It's only access requested data actions, data operations based on a given explicit instructions. So it's not about just identifying, single suspicious activity, but examining all the activities collectively to determine if they point to malicious intent or not. So using machine learning and AI is very important because they are the digital detective. They can sift through the, behaviors, identify the patterns and learn from them. By training AI and ML algorithm models with examples of the both legitimate and malicious activity, we can develop a system that becomes increasingly good at distinguishing between benign, means normal, and harmful files. So understanding the differentiating between malicious and benign file behaviors is very important. As cyber criminals are getting day by day and increasingly innovate, we must evolve our defenses. ML and AI is a powerful ally in this case. They allows us to identify and respond to threats with a greater speed and accuracy.
Lab session, behavioral malware detection. So in this session, I'm going to demonstrate behavioral malware detection using machine learning model here. Malware detection, it identifies malicious activity by analyzing the behavior of the program during the execution. Behavioral malware detection using ML is different from the signature-based detection. Signature-based detection, it relies on the known malware signatures and known rules. But whereas behavioral malware detection using ML, it analyzes the behavior, right? So that's the difference from the signature-based detection here. So before demonstrating our execution of the behavioral malware detection script, I will explain about the process that detecting malware using machine learning model, that specifically random forest classifier, because random forest classifier is good at in identifying the complex patterns from the programs. So here we'll be starting with that importing necessary libraries and simulating behavioral data, and that behavioral data includes features like a CPU usage and memory usage, disk read write, and network activity, and so on. And this data is then organized or converted into data frame, and features and labels are defined here in this. The labels are defined as labeled as benign or malware, right? So after creating the data frame and defining the features and labels, we'll split the data into training and testing sets here, and initialize the random forest classifier and trained with the training data, right? With the training data means it's defined features and labels here. Then classifier, after training, The classifier makes predictions on the test data, and the accuracy of these predictions is calculated and then outputted here. So finally, the trained classifier can be used to make new predictions and especially detection of the behavioral malwares on the unseen data. So this is what actually our flow and process here, and I will we will delve deeper into the code and implementation logic. So there I will also explain that step by step and then see how this logic is implemented there, right? And after walk through the code, then we will move on to the demonstration and check the output there, right? Let's move on to the source code. So here is the source code. This uses that random forest classifier, as I said. So it will detect the malware based on a behavior, file behavior, right? So and as I mentioned, this particular random forest classifier is a popular one, and it classifies behavior as either benign or malicious, right? Let's get started. So here we import necessary Python libraries and functions here, and the random forest classifier from sklearned.ensemble for our machine learning model, and train test split from sklearned model underscore selection, right, to divide our data into training and testing sets. Then accuracy score from sklearn.metrics to evaluate how well our model performs. And then pandas, and that is commonly we import as a PD that works with our data in table form, that is a data frame, right? Okay, then after importing the necessary libraries and functions, and we will move on to creating a data set or simulating that behavioral data here. But of course, this simulation of the behavioral data is for the demonstration purpose. But in real, in real world scenario, this data much more complex. And here, for the understanding and demonstration purpose, I have taken and features like CPU usage, memory usage, discrete write, and network activity, and then finally labeled them whether it is a benign or malware. 0 means for benign and 1 means for malware, right? Okay, so these are the behavior. For example, if you consider this particular column, first column, CPU usage 5, memory usage 20, discrete write to 50, network activity 5, and then that labeled as a 0, it means it's a benign 5. It's not a malicious activity. Let's look at malicious activity. CPU, it's like almost 90%. Here, if you look at last 4 records here, 90, 85, 92, 88. It means it's a high CPU usage and high memory usage and high discrete write and a higher network activity. So the behavior consisting these features and with especially with the high ranges are labeled as a malware typically, right? So this is how actually data is simulated here, and then after simulating behavioral data, we will move on to preparing the data here. We organize our simulated data into pandas data frame, and that makes it easier to manipulate and analyze. We then separate our data into features like called X and labels Y, and features are the behaviors we observe, that is like here CPU usage, memory usage, discrete write, and network activity, and these are the behaviors we observe, and labels that indicate whether those behaviors are benign or malicious here, right? Okay, so after features and labeling, and then we'll move on to splitting the data into training and testing set here using train test split functions. And here we testing set is 20% and training set is 50%, and for the so that we ensure we have taken some examples to assess our model here, right? After splitting the data, and we will move on to initializing the random forest classifier here. That is actual random forest classifier is initialized with a 50 trees. That is what we said, number of estimators equal to 50. It means 50 tree. More trees can improve the model accuracy, but also, of course, it also increase computational complexity. But at the cost of computational complexity, it improves that accuracy. So that's why we have chosen that higher number of trees, that is 50, right? So after initializing the random forest classifier, Then we train our classifier using the training the data, and this process means that a model learning to associate the features, that means behaviors, and with the labels, that is benign or malware here, right? So after training, we use our model to predict whether the behavior in the test set are benign or malicious. And finally, we calculate the accuracy of our predictions by comparing them to actual labels from the test set. Accuracy is like something percentage of predictions our model got it right, right? Then finally, we use trained model to make predictions on new and unseen behavioral data, and that would help to identify the malware in real scenarios. So this is a code where it demonstrates that how random forest classifier can be used to distinguish between benign and malicious computer behaviors data based on the observed the data, right? So of course, having understood this code, I hope you understand this code, and if you have any questions, and please post them in Q&A, and I'll get back to you on this implementation logic, right? Okay, having understood the code, we will move on to the demonstration. So where I will execute this script in the Kali Linux, where I will import the necessary libraries and then execute this particular script here. Then let's see what output we get it from that, right? So here is the Linux environment where I'm going to execute this particular script here. Let me show you the code, and the one which we have discussed just now. And you can also see here the same code which I've discussed, but only the difference here is that up to this point is the same, but here I have added some new data with the two samples here, and see how it is prediction, what is the prediction we are going to get it, right? So here are two samples, and CPU uses 10 and 80, memory uses 30, 70, disk read write 160, 600, network activity 10 and 35. So our basic understanding is that for the first behaviors, that I think it should be benign, because lower CPU usage, lower memory usage, lower disk read write activity, and lower network activity, right? But here the second set of features or behavior is higher consumption so of the resources. So I think that particular second prediction, I think it should be roughly that malware. The first one should be benign, and next one is that malware. That is what actually our guess and expectations. But let's see how well this model particularly model is trained, and then how well it will perform, all right, on unseen data, because this particular data is not seen here, and above the data is already seen and then trained with that, right? Okay, I'll move on to the execution. Let's compile execute this particular script. Behavior, yes, excellent, right? So here the output accuracy we got 100%, so that means that a random forest classifier model was able to perfectly classify all the behaviors in the test set as either benign or malware. Here is what we can understand from this result here. So the model correctly identified that every instance in the test set here. So here these CPU usage and memory usage, disk read write, network activity features provided strong indicator to distinguish between benign and malware behaviors in the simulated data set, right? So and another point is that this 100% accuracy reflects that quality and the simplicity of the simulated data. But actually, in real world scenarios, achieving 100% accuracy is extremely rare due to that complexity of the data, and also also the presence of noise. So here we have chosen quality data and simplistic data. So that's why we got 100%. But it's hard to achieve 100% in real world scenarios. So because of that, complexity of the data and the presence of the noise in that, right? So that's a difference here. Here the simulated data set not captured of the full complexity of the real world malware behavior, and that's where actually it led to overly optimistic result here, right? Because 100% accuracy seems ideal, but it looked like this particular model was trained. It's I think it's overfitting. The model got overfitting here, and if the model performance significantly right worse on the new and unseen data, then that is a overfitting question. But here overfitting occurs typically when model learns the training data too well, right? Including its noise and outliers, and so that that's where actually it makes it less generalizable, less prediction on the new data. But whereas come to this particular point, for this script here, I've chosen that quality and then simplistic data, and this random forest classifier completely trained with the training data too well, right? And also the testing data also is more or less is aligning to the training data, so that's why it is able to predict it very well. It performed very well. But actually this problem, this prediction will change in case if the training data will include that it's a noise and outliers, and if it's a complexity, and then that's when is really achieving 100% accuracy is really tough, right? So that's when it is a struggle in in generalizing or in predicting the new data, right? So right, so to validate that model effectiveness, right, it would be very important to test if it on a diverse and realistic data. So that is what very important, because real world data include more variability, and because and also too many variants of the malwares, and so that is what actually challenges the models here, right? Okay, so anyway, so here we have demonstrated that model ability to to apply what it has learned from the training data and see how we can make a prediction on the new and unseen malware data here, right? So this is what it is, and I hope you all got understanding. In case if you have any questions on this particular lab session, please post them in Q&A, and I'll get back to you on this. Lab session, ChatGPT condenses quick insights from complex security report. So in this lab session, I'm going to demonstrate how we can use ChatGPT that reads through long complex documents and gives us shorter version which is highlighting the main points and helps in identifying cybersecurity threats from the document and complex text. So before demonstration, I'll talk about the process, and here is a process which I have defined. Then afterwards I will talk about the implementation logic, and from there I'll take it to the demonstration stage, and where we will check the output and see how we can identify cyber threats from the complex text and documents using ChatGPT, right? So here is a flow chart which explain the process to summarize cybersecurity report using a ChatGPT, and we start with the process. Here is the process begins. Then set a API key. Then afterwards we'll define a function to summarize the report. And is there any report text? Yes. And checks if there is a text to summarize or not. That is the meaning of this is there report text. It means checks if there is a text to summarize report or not. If it is yes, proceed to summarize the report using the GPT 3.5 turbo model. If no, it returns unable to generate summary, and here we summarize the report using GPT 3.5 model, turbo model, and the model AI ChatGPT model, it attempts to summarize the provided text, and after that it checks did the API call success, checks if the summary was successfully generated. If it is yes, it extracts summary from the response and return it. If it is no, it says that return unable to generate the summary, and this here is the one the process ends. So to put it in simple terms, this workflow or process automates the process of summarizing a cybersecurity document using ChatGPT model. It checks if there is a text to summarize and uses the ChatGPT to generate a summary if possible, and handle cases where summary cannot be generated, right? I hope you understand this workflow and process here. Now I will move on to the implementation logic, where we will delve deeper into the code and then understand that, and after that I will move on to the demonstration. Here is a code where this Python script uses AI model, and it summarizes cybersecurity reports or articles. So this reads through long complex documents and gives us a shorter version, which is highlighting that main points. Then what is implementation logic here? So first we imported an OpenAI library, and OpenAI library is a package that allows this script to communicate with the OpenAI servers and use their AI model, that is GPT 3.5 turbo model. And before we use OpenAI services, we need to tell OpenAI who we are, right? So that we do this by setting our API key, which is like a secret password that gives us access to OpenAI models, right? That is a OpenAI key, API key. Then afterwards, define the function called summarize report. This function takes one parameter, that is a report text. It's the report text, which is the text of the cybersecurity report or a document which we want to summarize, right? Then we use OpenAI to summarize that. So let's understand that internals of this function. Here we use OpenAI completion.create function that will ask OpenAI model to summarize the text for us. And here we have specified that model or engine is GPT 3.5 turbo, and this is a specific version of OpenAI model, and that is good at understanding and generate the text, right? And also I have also provided the prompt that tells the ChatGPT model that what we want to do, what we want it to do, what we want ChatGPT to do that, right? Here the prompt is summarize, summarize detailed cybersecurity report or article using GPT 3.5 turbo model, right? Turbo model, and especially this means that here it is a prompt. You can check this. You are highly skilled AI trained to summarize cybersecurity report in a concise manner, right? In a concise manner. That's what it means. So now other parameters, like let's check the other parameters, right? Here just role is user and content is report text. That is a description or whatever that document or article or that complex text we are passing as an argument to this GPT 3.5 turbo model, right? And this model processes the report and returns a summary, and we extract this summary from the response and return it from this function, right? And after this, we have defined the example of how to use this function, and here I have defined some report text. That's a placeholder, right? And for the report, and here is the report here, okay? So this I'm not getting through this report, and after defining the report or summary report, pass on to the summarize report function, where that gets the summary. That is a concise summary, not this much information. Suppose let us say this might be big document or maybe complex text, but where we get a very summarized and concise summary, we get it, that it get printed out, right? So it's very helpful for the quick understanding complex information without having to read through everything by ourselves, right? So it just gives us quick glance, and it helps us to understand complex information without going through that complete information or complex data, right? I hope you understand this. So if you have any questions, please post in Q&A. I'll get back to you. And then let's move on to the demonstration, where I will execute this particular script, and only in that demonstration where I have replaced with my own OpenAI API key, and rest of the code as it is. It's the same, right? Okay, let's move on to the demonstration where I will execute this particular script, and then see the output and what we insights we get it, and what sort of concise summary we get it from that. Let's check that. So let's execute. Here is the Kali Linux environment where I've imported OpenAI library, and then I'm going to execute this particular script. Okay, and Python 3, yes. Malware summary report cgpt.py. This is the script here, which I'm going to execute it. Let's run it. Right. Excellent. Right. So here is the summary of the report, and you would have seen that in the code where it's a very big text, which has a lot of information, but that may not very required for us to get a quick understanding from this complex information. But here it is, we got through that shorter version, which is highlighted that main points, and here the summary tells us that detailed report was analyzed about cyber attack on a company named Acme Corporation, right? And so you can see here a recent cyber attack on Acme Corporation involves sophisticated phishing scheme that allowed attackers to deploy ransomware on the company internal network. The ransomware used in the attack is similar to Ryuk, indicating possible connection to a known cyber criminal group. So this incident underscores the importance of enhancing employee training on phishing and implementing stronger network security measures, right? So this kind of information is that here the takeaway from this is that we need to better train employees on how to spot these tricks, phishing, right, and strengthen the defenses of the company computer networks. That is information we quickly got from this concise summary. I hope you understand that. So how really, this tool would really helps us to get a quick understanding of complex information from this, right, using ChatGPT. So sometimes by going through lots of information, and then we may get confused or we may not get a clear idea. But here is the one ChatGPT helps us, automating this, and helps us to extracting and summarizing key information that really helps us to what exactly which we need to focus on to strengthen the defense of the organization computer networks. So that's the key information here, right? I hope you understand this, right? If you have any questions, and please post in Q&A and I'll get back to you.
Attribution modeling in malware analysis, identifying the puppet masters behind the strings. Catching malware is just the first step, but we need to know who crafted it and from where it was launched. This backstory is very much crucial for not only to prevent future cybercrime but also to take legal action. That's where attribution modeling steps in. It's an art of tracing digital footprints back to the cyber culprit. How does AI fit into this cyber puzzle? Right? AI sifts through mountains of digital evidence in the blink of an eye. It spots patterns in a malware course, patterns so faint that even the sharpest human eyes might miss them. AI brings algorithms like support vector machines, neural networks, random forest and all. So they can be used to transform the art of attribution into a science. It means it can spot patterns in the malware code, right? It can trace back to the origin. So that's what attribution modeling would help us in malware analysis. So we need to hunt for the digital fingerprints, right? So AI delve into these internals of the code, the structure of the code, the naming convention, the types of the functions used. That's how it unravel the identity of the malware author, right? It can figure out the identity of the malware author. So to train our AI detective, we need a database of past malware cases, complete with the signatures of their known authors. So the AI detective, it goes through over these cases, learns to associate specific coding patterns with a specific cyber offenders, right? So training is good, but the real test comes when the AI detective faces a piece of malware it has never seen before. So we test its accuracy, its precision, and its recall. So here we do not want, I mean, we want detective that not only catch but also trace it. Let's say when a new malware threat emerges, so AI gets to the work, analyzes the code, compare it to its database of past malware signatures, and then point the finger at who might be behind it. So this information is very, very, very important for the cybersecurity professionals. Let's take a look at this example here. Here is a malware sample, okay, and this malware, sneaks into systems and with a feature extraction, extract coding style, API calls, and some unique errors, right? So here, and this we can derive the style pattern and a style pattern from this coding style, and from the API calls we understand API usage, and from the unique errors we also understand error pattern analysis, right? So style pattern analysis, API usage analysis, error pattern analysis fed to the AI model here, right? So this AI model, or we say AI detective, this examining the style pattern, API usage, error pattern, right? And it notices, it uses some peculiar sequence of APIs or commands, right? Similar to previous malware known to originate from a particular hacker group. So here, so while predicting it, it also identify the author, it also identify the origin, right? And then it report it and it take necessary action. It can be reported to law enforcement, and also we can take appropriate cybersecurity measures, right? So we can strengthen its defenses against that specific threat here. So by extracting these features, right, and by predicting author and origin, so AI attributes to this particular group. So then by understanding the origin and authors, so we understand the next moves taken by the hacker. But that's what the behavior it is. And also we get to know what is the next action the attacker is going to take. So then once we get to know the origin and the author by attributing to this specific group, and we can come up with the appropriate cybersecurity measures. So this is how actually we can strengthen our defenses against that specific threat. So attribution modeling in malware analysis is not without its challenges. There are, challenges, and there are risk of misattribution, right, which has some serious consequences. So that we should take care. Attribution modeling in malware analysis is a testament to how AI is reshaping our approach to cybersecurity. It's a deep, intricate field where ML and AI meets investigative analysis, and together it opens new frontiers in cyber defense. So to understand better, anyway, in our next sessions, I will demonstrate this attribution modeling in upcoming lab sessions. If you have any questions, please post in Q&A and I'll get back to you as soon as I can.
Lab session, attribution modeling in malware analysis using support vector machine. So in this lab session, I'm going to demonstrate how we can use how SVM is helpful in attribution modeling in malware analysis and in identifying the likely author of the malware sample. So here author means that it means it is implies or it refers to the individual or group responsible for creating the malwares. So here that is the intent here in this lab session where I'm going to use SVM to identify the likely author for the malware samples, right? Okay, so so here is a diagram that explains the process of using SVMs to identify the likely author of the malware sample here, right? And first we extract the feature from a malware sample, and these features are static, meaning they don't change and are extracted without executing the malware. So these features like such as API calls, file attributes and coding patterns and so on. Anyway, we will talk more about the features in the implementation logic. And after extracting the static features, this data, these features serves as a, foundation for the entire attribution modeling process here, right? And the static features from the malware samples are used to train the SVM model. And this training, it means that model learning to distinguish between different malware authors based on the features, right? And after training, the model can take a new malware sample and extract its features and then predict the author based on what it learned during the training. And the prediction may be made by the SVM model, is that can be used for further analysis. Whatever that SVM predict the author, that can be used for further analysis and reporting, because that can provide some actionable insights and like understanding the tactics, techniques and procedures of a specific malware authors. So once we get to know the malware authors, and it is easy for us to understand the tactics, techniques and procedures of the specific malware authors used it, because we can also refer that MITRE framework and then understand more about that particular author. So here the intent is that based on the features, and we need to predict the likely author for that malware samples, right? I hope you understand this the process here. Then now we will move on to the implementation logic, where we'll delve deeper into it. Here is a code, it's a Python script, where we use SQL, scikit-learn library to classify malware samples based on their features and predict their authors using SVM classifier. And we begin by importing, SVC, that means support vector classifier from sklearn.svm. And then that is a SVM algorithm used for the classification. And pandas, it's a library useful for the data manipulations and analysis. So here is a sample data we prepared, and that contain the features of a different malware samples, such as API call patterns, code complexity, and string encoding, file size, control flow patterns, and the corresponding authors here. So here the corresponding authors. So here author A, typically use this kind of features, like API call pattern is 1, code complexity 5, string encode is in 1, file size is 200, control flow is 3, right? This is the typical features of the author A. And same author B, when author B develops that malware samples, the corresponding API call pattern and code complex string encoding, file size, control flow is in the second column here, 230 210 2, right? This is, and then same way author A and author C and author A, right? So these are the authors. They use specific features when they develop that particular malware samples, right? So now this data we convert into the pandas data frame DF. That's a tabular data structure. And as I mentioned, here we will extract features and target variable. Here by dropping the author, we extract all the features that is belong to X, and then here we will extract only author variable values, that is a Y, right? And here the author means that it's it's an individual or a group that is responsible for creating the malwares, right? And the author column in the data dictionary, that it contains the label, that is where actually used to identify the which author from a, right? That's how it is identified. And from a known set of authors and created each malware samples, it will identify the author. So these labels are used by the SVM classifier as a target variable to learn from the training data, that is the features of each malware sample, and it makes a prediction on the new and unlabeled data, and then identify based on the unlabeled data means based on the features it will identify and predict new author, right? Its author. So here we use SVM classifier to find the patterns in the features that are associated with each author here. And when new malware samples are presented, right, to the trained classifier without an author label, the classifier predicts which author is most likely to have created that each new sample based on the learned patterns, right? So this this can be very useful tool in cyber forensics to attribute malware to its source, right? It means like potentially we can track the activities of the specific malicious actors. It means based on certain features we can even trace the attacker source. It means attacker threat actor, malicious actor we can trace back, right? So this is so by tracing back or by understanding the attacker source and threat actor, we can understand tactic and techniques and procedures, and so that we can take appropriate security measures, and we can even prevent future attacks, right? So this is what the benefit of this this attribution modeling, right? So after creating it feature selections, and we the features are the data points the model will use to learn the patterns, and target variable is the one what the model will predict it, right? So, and after features and target variable, we initialize the support vector classifier, and that is trained using the dot fit methods. So here is the one we will train that SVM based on the features X and target variable Y, and this process it learns from the sample data, and also it will find the boundary that separate the classes, especially in a SVM. So, and in this case that authors and based on the features. I mean this is how actually SVM it works, right? And after training the model, we will define a new test data, that is with a new malware sample with a unique features here, and this but here there are no author labels, and then we convert this into a new data frame, and then CLF.predict is used to predict the authors of the new malware samples with the .predict method, and that uses the patterns the model learned during the training, so that we can infer that model can infer the authors of the new sample based on their features. Then after predicting the likely author of the new malware samples, it displays the predictions here, and it prints out the prediction with a simple for loop that enumerates through the prediction list and displays which author is likely associated with each new malware samples. So I hope you understand this. So here to summarize it, first to train the model using the known data, and then applies this model to make a predictions on the new data, right? So that way once we train the model, we can deploy this in the real world applications for cyber forensics, so that where we can trace back the it helps to trace that attacker source or threat actors, right? So I hope you understand the code, and then we will move on to the demonstration where I will execute this particular script and then see what insights we can get it, and what we can deduce from that particular output. So here is Kali Linux environment, so where we will execute this particular script, and let me show you the script here, and this is the code which we have discussed just now, and so here is the code where we have discussed just now, the same code which I am going to execute. So let me run this code Python 3 attribution model 1.py. First let me clear off this so that we'll have a clear visibility. So Python 3 and attribution model 1.py, excellent, right? So here it predicted author of the new malware samples, sample 1 author A, sample 2 author A. So here successfully this SVM support vector machine model successfully predicted that likely authors for the new malware samples. So according to the model, both sample 1 and sample 2 are likely authored by the author A. It means author A is a threat actor. Um, so that particular threat actor is responsible for the creation of these two malware samples. So this is what we understand from this output, right? So, and from this output, right, we can also understand that SVM classifier, it was trained on a set of known malware samples and it has predicted likely authors, that means author A of two new malware samples, right? So the SVM has attributed both new samples to author A. It means, so the SVM is clearly telling us that the two new malware samples are authored by author A. It means author A has created these two new malware samples. It means it's two new malware samples are belong to author A, right? So it clearly says that the features of these two new samples closely match the patterns are associated with the author A as learned during that model training phase, right? So based on the model training, it's clearly telling that the features of these two new samples are matching the patterns what it learned during the training. So this kind of prediction, it helps malware analyst in pinpointing the source of new malware and understanding the techniques or patterns which are very common to the malware created by author A in this example, right? So, and also you need to remember that machine learning models can provide valuable insights, no doubt in it, but their prediction should also be uh, analyzed by us, by human, by cybersecurity professionals, with further analysis and evidence, especially in the real world, applications, security applications, because where accuracy is critical. So our judgment is again very much important in this. Though machine learning models are pinpointing the source, right? So that is always you need to remember. There is no doubt in that this particular, machine learning models are helping us to trace the attacker source, and that is really good thing. But at the same time, our judgment also is required on this after, to evaluate that, to take it further, right? But in case if you find that the model is not as accurate as you expected, you can also consider that, certain steps to improve its performance, like a feature engineering where you can add more features. Because here for the demonstration purpose I have chosen some 5-6 features here, but you can also add more features that could be indicative of other unique characteristics. That is really important, right? And another important point is that hyperparameter tuning, because experiment with the different kernel functions and regularization parameter in the SVM model is very very important, because that play very critical role in improving the accuracy, because that is what actually exactly it learns that complex patterns. So these hyperparameters are really helps in learning the complex patterns. So that's why regularization parameters and cardinal functions should be fine-tuned to improve the model, right? So that also second thing which you need to take care, consider in order to improve its performance. And third point is more data. The more data you have, the better the model can learn the different distinguishing or unique features of each malware authors. That is more very important, because the more data you have, the more it's better, right? And fourth thing is cross validation. Use cross validation techniques to get more generalized model, so that it can work across unseen and new data, right? So cross validation is very very important. And fifth thing is class balancing. Class balancing is if the data set is imbalanced, and you need to try to balance it with ensure that no bias in it, and add as much as balanced data. And also you can consider using techniques like a SMOT, SMOTE, right? SMOT technique or class weighting, so that it can balance it out, right? So okay, so remember, machine learning models or neural networks or deep learning models are iterative process, and it always requires or takes several rounds of refining to get a model that perform well in real world scenarios. I hope you understand this demonstration. So if you have any questions, and please post in Q&A, and I'll get back to you as soon as I can. And we can also have, sometimes you might have some doubts, and then you can post them in Q&A, and that would help to bring out additional more insights into it, and that's where we will enrich our knowledge. Okay, I hope you got it. And also, here I've chosen the SVM is very good in classifying and regression, and also SVM is really good at in identifying the complex patterns. But apart from the SVM, you can also try with other machine learning model and see how well which can how well it can perform that in these particular scenarios, right? And also here we can also consider threat intelligence data, and that particular threat intelligence data also we can input this particular training, and so that we will have a more data, and where it can really works in or helps in tracing that attacker source or threat actor. Because threat intelligence data also, it consists lots of it's a unique characteristics, and then along with that particular data is even associated or mapped to that particular threat actor and threat group. So that kind of data, if you can bring in and then train these models, and that really, I'm pretty sure that this would play a great role in cyber forensics. Lab session: automating IOC, indicator of compromises extraction, with ChatGPT for cybersecurity analysis. IOC extraction is very important for the malware analysis. So in this lab session, I'm going to talk about workflow and implementation logic, and then demonstration of this particular implementation logic, right? So before getting into the workflow here, let us talk about why do we need indicator of compromises for malware analysis. What is the importance of it, right? What is the essence of it? So indicator of compromises are like a clues or fingerprints that malware leaves behind. I'll give you an example. Imagine you are a detective trying to solve a mystery. So these indicator of compromises are your key evidence. Indicator of compromises help us figure out if a computer or a system or a network has been hacked by the attacker, and it shows us traces of the malware actions. Just like detectives use clues to catch criminals, something like that, right? So what are those indicator of compromises? Like IP addresses, URLs, file hashes, suspicious behavior, registry entries, and so on. So these are the indicator of compromises which we need to analyze the malware in deep, right? So we need evidence, key evidence. They are the key evidence which will tell us the traces of the malware actions. So they help us. Indicator of compromises helps us to protect our computer and information from bad actors. So IOCs are super important because they help us quickly understand and fix security problems before they can cause more damage. So this is the essence and importance of IOC extraction for the malware or cybersecurity analysis. So that is why we need, how can we need a tool to automate IOC extraction with a, right? So here ChatGPT we are going to utilize ChatGPT for IOC extraction and in automated way. I hope you understand that, right? So here is the workflow which I am going to talk about how we can extract, IOC extraction. So here is a flow chart which describes that flow process of generating indicator of compromises from a textual description, right, using ChatGPT. And here is a process begins, and next we set an API key. So this API key for OpenAI, we set up, we will assign that. So this particular function and the API key is necessary for authentication with OpenAI service. All right. And after assigning API key, we'll move on to defining the function that generate IOCs from a description, right? And then it check the description. If there is a description provided, yes. If it is no, return no description provided, and then end the process. If it is yes, right, it proceed to generate IOCs. So here we generate IOCs using GPT 3.5 Turbo. That's a model, AI model used to generate IOCs based on the provided description, right? If API call success, yes, it extract the IOCs from the response. If it is no, it handle error and return error message, right? So if it is yes, it extract IOCs from the response and return IOCs here, right? The extracted IOCs are written, and here is the process ends. So here is this flow chart. It highlights how we can use AI model to create a list of potential security threats, that is IOCs, from a given description of the malware behavior, right? I hope you understand the workflow here and process here. And after this, and then we will move on to the implementation logic, where we will delve deeper into the code. Then we understand the step by step, and I will walk through the code so that you will have a better understanding. Then after implementation logic understanding, then we will move on to the demonstration, where we will execute that script and then see the output, right? Here is the code. So here is a code we use with a a GPT 3.5 Turbo model to analyze that textual description of the malware behavior, and then generate a list of indicator of compromises. And IOCs are very crucial information that we can use it to detect potential security breaches or infections in the network or a system, right? Okay, so let's begin. So here we import the OpenAI library and set up AI API key that is necessary for authentication with the OpenAI service. And then as we talked about this in a flowchart and process, and here is the one actually we have defined the function that is generate IOCs from a description. And this one, it takes a string description as an input, and this description details the malware behaviors or characteristics here. That the same description is provided to the model here, right? To the OpenAI API, and where the GPT 3.5 Turbo model is used here, right? And inside this function, yes, as I mentioned, that's a GPT 3.5 Turbo model, and this sends chart like a prompt to the model and ask the model to act as a cybersecurity analyst and identify IOCs based on the provided description. So that is what it is, right? And then function process the model response once that OpenAI API return the response, and then the model response will be processed and extract and return the text that presumably contains the IOCs. If no IOCs generated or error occurs, it handle these scenarios here gracefully by returning an appropriate error message saying that error occurred while processing the request, right? So finally, and it's a sample usage of the function where malware description is provided here, and that generated IOCs are printed here, right? So that description okay, is passed on to this generate IOCs from the description API. That return the response which contain the IOCs that get printed out here, right? Okay, so here is a description. The malware contains command and control server located at so and so IP address. It also creates a registry entry to ensure persistence after reboot. And the malware signature include the hash value ABC123, right? And from this description, it should extract IOCs. That is the requirement we need it from the ChatGPT, right? I hope you understand the code. It's a very simple code. And then now we will move on to the demonstration where I will execute the script, and only the difference is that where I will replace this particular string with my own OpenAI API key and then execute that script there, right? And then we'll see what kind of output we generated and then what we can get the insight from that. Here is the Linux environment where Kali Linux, where I'm going to run a Python script, the script which we have discussed just now. So I'm going to run the script here. Let's run this. As I mentioned, that script, only the difference between the one which we have talked about and the one which I'm running here, only OpenAI API key, rest of the code as it is. Okay, and now we got a output. Wonderful. So here this provides, and this output provides 3 indicator of compromises which are associated with the malware incident that was explained in the description. So here, utilizing these IOCs, we can improve cybersecurity posture by utilizing them to detect, respond to, and mitigate threats more efficiently, because we know the 3 key indicator of compromises, because they are the key information, they are the key evidence, right? And we can see how we can leverage and each of these identified IOCs for improving security controls and security posture, right? Let's talk about the first one. So here is one IP address, and that is a command and control server. So here, this would helps that we will configure the security controls like a firewall and network access controls, uh, defenses, to block or monitor traffic to and from this particular command and control server IP address. So here is IP address is 192.168.1.1, and this is CNC IP address. So here we are, based on this information, we will configure this particular IP address in a firewall and NACE, network access controls, where we'll configure such that we can block or monitor the traffic to and from this IP address. That's the key information where which is key clue we got from this. So this is the information which we are going to configure it in firewall and a network access control, where we can block or monitor that, right? To and from this IP address, right? So this can prevent the malware from communicating with its command and control server, effectively neutralizing, neutralizing the neutralizing the ability to receive instructions or exfiltrate the data from the command and control server and exfiltrate data from the victim machine. So this we can effectively neutralize that, right? So that is one of the key points here that have helped us. Next one is threat intelligence sharing this IP address with the threat intelligence platforms and communities. We are contributing to a broader understanding of the threat landscape, so that helps others to defend against these and potential related threats as IP address is concerned. This IP address is concerned, right? That's another advantage. And third thing is incident analysis, where we investigate any connection attempt or traffic to this particular IP address in the network log. So this helps us to identify infected missions and the scope of the compromise based on this particular key evidence. So that is this particular key piece of the evidence, right? Next, another IOC, look at it, registry entry, where registry entry created by the malware for persistence after reboot. This is key information. So here we use EDR tools, endpoint detection and response tools, to scan for and remove any unauthorized registry entries. And many EDR solutions can automate this process. We quickly identify and mitigate the persistence mechanisms that are used by the malware, just being based on this key evidence clue, and we are going to configure it in a EDR tool so that it can scan and remove unauthorized registry entries. That's advantage based on second key clue. Another advantage is that policy and configuration management, where we review and tighten, group policy settings and configuration management practices so that it restrict unauthorized changes to the registry. This can prevent the malware from establishing persistence mechanism in the first place, right? So that's our advantage. And then another last thing is that we educate users and employees about the importance of not granting administrative rights to unknown applications and the risk associated with the phishing emails, right? They are the one actually which lead to malware infections, and that can modify the registry for the persistence, right? So based on this information, we will educate the users and the employees. That's the key things, and which we are going to, this is a key clue which we are going to use for the education as well, awareness as well, right? And third key indicator of compromise is hash value ABC123. That's a malware signature, antivirus and anti-malware solutions where we update those solutions. We update antivirus and anti-malware solutions with this hash value to detect and quarantine. And quarantine means isolate, and isolate the associated malware file, right? So here we detect and isolate the associated malware file. And many security solutions allows us to add custom signatures or indicator for, for detecting this kind of signatures, right? So this is advantage is that. And another advantage based on this key IOC is that, we use this hash value in digital forensic investigation to search for the malware file across systems in the network. This helps us to understand the spread and in amount of infection and impact of the malware, and also identify the entry point and method of infection. So this is another advantage where we use it for the digital forensics. And information sharing, and this we will share the hash value with the industry peers or threat intelligence or cybersecurity information sharing platforms. So we will share this similar to sharing the IP address. We will also share that hash value, and this helps and contributes to collective defense effort by and enable others to detect and defend against the malware, in their systems. So this is another advantage, right? So here, based on these IOCs, it helps to continuous monitoring and update our incident response plan, right, to deal with the infection that match these IOCs, and also regularly, conduct security awareness or, sessions or training, right, and about like information on the latest threats and how to avoid them, right, and also importance of every user in maintaining organizational security, right. By implementing these measures, we can significantly reduce the risk posed by the identified malware based on these IOCs and enhance or improve our organization's overall security posture. So this is what actually, which we are going to utilize the IOCs, and it helps us, right? So here is the one actually ChatGPT helps us in automating IOC extractions. I hope you understand this, right? So if you have any questions with respect to this, please post them in Q&A and I'll get back to you.
Detecting encrypted malware traffic. So here we need to spot malwares within the encrypted traffic. We cannot open that encrypted traffic and decrypt it and then look for or spot for the malwares, isn't it? So let's take a look at this example here. Typically, source, for example, like within the corporate network, or maybe this is from something Google servers, right? So when you want a Google search, then it's like, downloading is more, right? So here, when you page refresh or initial page load, and you can see that this like from the destination to the source here. But whereas you can look at this, diagram here, the source is, sending more traffic, more data to the destination, right? So here, if you think that maybe the source could be the maybe victim or compromised mission, or maybe if that is sending a lot of data to the outside rather than downloading, like as you see here, right? So if it is uploading or maybe sending more data to the outside, then that could be the one, suspicious one, right? So here you can also see some specific pattern here. receive some fixed messages, that is command and control messages from the destination to the source. Maybe you can think that this may be the machines which are controlled by the attacker, and from where you the victim gets that fixed messages, like that is command and control messages, and in response to that, and if victim made a compromised mission or maybe sending more data to the outside world, so then that's where one suspicious pattern here, right? So that's how we need to observe, and that's how we can use packet lengths and times to guess what is happening inside encrypted traffic here. So here we will see that what is a packet length, like whether it is whatever that is going out. See, when you look for the Google search, then you will send a smaller request, but whereas you get initial page load is that is too heavy, right? But whereas in this case, where in respond to fixed command and control messages, and the victim or compromised machine is sending more data to the outside world, right? So here is a one where we can use that packet length and times to guess whether it is if something is going on inside the encrypted traffic. So every data transmission over the network that involves packets, isn't it? So by analyzing the size, that is length of these packets, and the time intervals between uh, between their arrivals, like inter-arrival times, like between command and control messages, if there is a inter-time arrivals. So we can infer certain behavioral characteristics of the transmitted data. Let us say, if there is some, fixed time, or maybe between the fixed messages, right? There is inter-arrival time. So based on that, and if the outgoing data, that is packet length, is heavy and more, and then we can see that this is one behavioral pattern where we can infer certain behavioral characteristics of this transmitted data, right? So as I mentioned here, we have considered two different TLS sessions here. One from that regular Google search, and this is another one initiated by the malware named Best of Era, right? So the Google search here, it shows the typical pattern of small client request here, small client request, and followed by large server response. This is the large server response from the server to the client, but whereas client to the server, there is a small client request here, right? So in this when in contrast to this here, the best of era initiated connection, right? It shows that data exploitation pattern, that is like a data sending out. So where data is being sent out to the external server here. Okay, having understood this, and another important aspect is where the fingerprinting, right? It's a signature. Maybe we can say it's a spy signature, right? So in the world of encrypted traffic, we have something called a handshaking between a client and server. So that here, client hello message, and then after that server hello, and then client key exchange, right? And change ciphertext, and this is finished here. So here clients will send all its um, interest in connection creation. So then after that server send with this key exchange details, and then based on this whether client client can support. The reason is that the handshake phase, this is the handshake phase between the client and server, that provides valuable metadata, right? That we can use it for the analysis. So here the client and server has used the TLS protocol, and that is especially during that handshake phase. And here the client hello message in this TLS handshake, this contains the information about cipher suits and extensions, and that is supported by the client. So whatever the client support that cipher suits and extension, so that it will mention that in the client hello message and send it to the server, right? So here by analyzing this, we can potentially identify the type of application or even specific malware communicating over the encrypted channel here, right? Because why we are interested is that different applications and different devices have a different preferences for cipher suits. So a desktop browser might prefer robust encryption algorithms, right? While mobile app might opt for more efficient one. So malware, especially maybe if it uses default settings of popular libraries like OpenSSL, so that can have some unique fingerprints that can be detected. So by inferring into the this handshake messages and based on certain metadata, right here, if you can look at here, client suits, right, cipher suits, client cipher suits, and by inferring this data, and we can understand like what kind of browser it is. And typically malware cases, they might use some default settings, right? So that's when actually we understand the signatures and we understand the pattern. So here, after client sending the server, and server based on that client supported cipher suits and extensions, it will respond back with that. And then afterwards they exchange the keys, and so they agreed on that cipher suit and extensions, and established that key both the sides. And then they start transmitting the data by encrypting it. And client and server both will have shared secret key through that public keys, public and private keys, and they derive the shared secret key between the client and server. And after that, using that shared secret key, client can encrypt or decrypt it, or server also can encrypt and decrypt it, right? So by looking at that client and server handshaking messages and unique cipher suit and extensions, and by inferring that, then we understand that what, and there is a pattern for the malware or attackers using that default settings and cipher suits and extension. So that particular metadata would help us in spotting malwares or what's happening inside that encrypted traffic. So based on packet lengths and times and handshaking features and metadata, and using these features, and we can infer what's happening and what's going on inside that encrypted traffic, right? So here now, so this is where actually machine learning and AI come to the risk. And machine learning is like having a super smart assistant, right? And that can remember and analyze every single handshake it has seen. By feeding this information about all different kinds of handshakes, packet sizes, times, packet lengths, packet times, and those client hello details, that is a handshake details and metadata. And so ML and AI gets really good at spotting that spice, and figure out like what's happening inside that encrypted traffic, right? So here features are very much crucial for any machine learning and AI model. So let me repeat it again. So for the encrypted traffic analysis, AI and ML algorithms needs features like number of packets, number of bytes sent, and the packet duration and packet lengths, and inter-arrival times between the packets, and sequence of packet and lengths, and analyzing the sizes of the packet in flow, and TLS metadata. So this information from the handshake messages, that client hello messages like a cipher suits and extensions, using all these features, and AI and ML can really good at spotting the malwares or bad data within that encrypted traffic. So we take all these clues, the packet sizes, the timing, handshake details, and we give it to the AI and ML algorithm that's good at finding the patterns. Maybe let us say you can use the random forest algorithms, or even deep neural network. So they're all look for the different clues and then putting it all together to say that yes, that's how they can figure out, right? So the bottom line is that encryption is making detection of the malware is harder, but not impossible, right? So by using smart observations, understanding that handshakes, and employing machine learning and AI algorithms, we can still catch the malware without even opening it, without even decrypting it, right? So this is how actually we get better at detecting the malware, gets better at hiding, right? So this is what it happens, and that's how actually we can detect the malwares inside any encrypted traffic. Malware detection in encrypted traffic without decryption. Let's say when you send a message on WhatsApp or buy something online, encryption keeps that information safe. But what if someone could pass secret messages or even threats in code, in encrypted message. That's the challenge we face with the malware in encrypted traffic. Why encrypted traffic? Because you need to protect user privacy and data integrity. But at the same time, downside with it, it hides malicious activities. I'll give you an example. Imagine you have a pile of sealed letters. You need to figure out if anyone contains secret plot, but you can't open them. That's a private. So encrypted traffic is like those sealed letters. We need to detect any hidden malware or malicious activity without breaking the seal. That's the challenge we have. Here the challenge is traditional tools cannot inspect that without decryption, and encryption makes traffic black box. So that's a challenge. Without breaking it, without opening it, we need to still spot that malwares inside that. That's a challenge we face. That's where AI comes to handy. Features and metadata. Here we need to gather the clues. That means metadata analysis. Let us going back to the same example. Even with the letters sealed, there are clues. How heavy is that letter? When was it sent? Who is sending and receiving them? Similarly, with encrypted data, we can analyze metadata such as packet size and timing. It means it's like noticing someone sends very heavy letter every night at midnight. Odd, isn't it? This could suggest someone is sending out stolen information. So that's a packet size and timing. And protocol and port information. Let's take that example, same example. If a letter is supposed to go through the mail, but it's being hand delivered, that's unusual, isn't it? So we look for the data packets doing things they are not supposed to do. That's a protocol and port information. Certificate details. This is like a checking the postmark on a letter for authenticity. If it is from a place known for sending spam, it's a suspicious, isn't it? That's a certificate details. Sequence of packet exchanges. If every time someone receives a letter, they immediately send out 10 more, that's a pattern worth noting. Traffic volume. A sudden flood of letters from one address might mean something significant is happening, isn't it? So we need to check for the traffic volume. Endpoint details. If a trusted friend suddenly starts getting letters from someone known for bad news, it could mean trouble. So these are the metadata and features we consider, we take into analysis, and then figure out, we can draw some pattern and we can spot something malicious without even decrypting it based on the features and metadata, right? Okay, another aspect is for the malware detection in encrypted traffic is machine learning to the rescue. That AI is rescue. So here is where we get clever. We use machine learning and AI algorithms to pick up on these clues. These clues means whatever we have performed that features and metadata analysis, and those clues we use and learn what normal and suspicious look like. Over time, they get better. AI and machine learning algorithms get better at sniffing out hidden malware, like a detective learning the tricks of a master spy, right? So it recognizes subtle patterns and train on vast data sets, right? And based on these clues, which learn from the features and metadata of the packets, right? And then deep packet inspection. Deep packet inspection is like a quickly flipping through the edges of the letter to see if there is anything heavy or unusual without opening them. So of course it respects privacy, but still keeps an eye for anything out of that place. Looks at packet header and inspect initial handshakes, right? So that is what actually which we need to look at it, deep packet inspection. But for the encrypted traffic, there will be some initial negotiation, initial handshake, right, through which the keys gets exchanged between the sender and receiver. And after that, it starts encrypting and decrypting the traffic between sender and receivers. So prior to that, there is initial handshake. So we inspect that initial handshake and looks at packet headers and features and metadata, all of them, as part of the deep packet inspections. So that gives some clues about that. Still, without decrypting it, we need to respect privacy, isn't it? The ethical dilemma: privacy versus security, right? So there are two things. Decrypting violates privacy, of course, by decrypting it, because you will see the information, so that violates privacy. And the second point is that balance security and privacy. Here we must walk a tightrope between keeping everyone safe from the digital threats and at the same time respect the privacy sealed within the encrypted data. So it's a challenging balance, but we must navigate with a care and responsibility. That's when actually we need this malware detection in encrypted traffic without decryption, using AI and machine learning features and metadata, right? To summarize, detecting malware in encrypted traffic is like being a code breaker and detective rolled into one. We look for unusual patterns, train our system to recognize them, and always stay alert for anything that doesn't quite fit, right? It's a complex puzzle. But with the machine learning and AI and careful analysis, we can protect. We can spot the malwares in encrypted traffic, and without breaking it and without violating the privacy.
Lab session: Malware detection in encrypted traffic. In this lab session, I am going to demonstrate detecting malware in encrypted traffic without decrypting it. In traditional environment, there was a scenarios where detecting malware in encrypted traffic requires decryption, but that would lead to privacy issues. It's a compromising that user privacy. But whereas with advanced techniques like using AI and ML, we can detect the malware in encrypted traffic without decryption. That's really important technique where we can detect it. And most of the case, decryption also may not be possible, because unless you have some keys, private keys, you cannot decrypt it, right? So here we will overcome such issues here with the using advanced AI and ML techniques. Let's understand that. And also, as we in a previous sessions we have already discussed about this, but in this lab session I am going to demonstrate detecting malware in encrypted traffic without decryption. Let's understand these diagrams and workflows here so that you will understand better. Let's look at this particular diagram. How can we inspect encrypted traffic? So here this explains methods for the inspecting encrypted internet traffic. Encrypted traffic is the data that's been converted into a code to prevent unauthorized access, isn't it? But there are still ways to learn about it without breaking the encryption and detect the malwares. Let's delve deeper into this. Here, it examines that initial data packet unencrypted fields. You might be wondering, without even keys, how can we inspect encrypted traffic, right? So there is one important data we can examine without not even looking at encrypted data. That is initial data packets, unencrypted fields. Those messages would help to establish the exchanges, establish the connection between the client and server, isn't it? Even though data is encrypted. So here certain information like TLS header, transport layer security header, because that TLS is responsible for encrypting and decrypting the data, and it transfer the data securely. So here TLS header includes details like a server name, certificate information, right, and many other things, and also IP addresses, port numbers, protocols. By looking at this, we can get general idea of where the data is coming from and where it is supposed to go. So we can make the most of the unencrypted fields and then learn the information that where the data is coming from and where it is data is going to. So that information we can get it by inspecting at initial data packet. And also another aspect we can understand without decrypting it, that is sequence of packets, lengths and times. So here it is analyzing sequence of packets and lengths and times by observing how big the data packets are and the timing between those packets. So we can guess the type of content being sent. I'll give you an example. A video might have a larger and more regular packets, right, compared to text chart. So by observing the size of the data packet and the timing between them, that we understand, we can guess that what sort of traffic is going through that. So we can identify the content type through the size and timing of the packets, right? You can also look down here. So here, client and server here, right? From the server, it receives that. So here, the top one, it receives the data from the internet, like let us say when you search Google or whatever it is. But here, there is a data exfiltration, there is a command and control messages. Command control messages from the attackers and data exfiltration where after compromising the victim is sending the data to the outside world. So here, the client has received command and control messages from the server. Maybe you can say that is attacker or whatever. So the server is sending command and control messages to the client, and in response to that, it is exfiltrating. It is transferring the data from the victim to the attacker machine here. This is that. But normally it is the other way around, isn't it? From the Google, suppose it is someone, maybe client or user will access that. It will get the data more from the server, but not from the client. But here, server or attacker control machine sending command and control messages. So in corresponding to that, in response to that, and victim is transferring the data to this. So by observing the content type through the size and timing of the packets, we can understand that, what sort of content it is going through that. By observing sequence of packet lengths and times. So this is one of the aspects which we need to look at it, along with the initial data packet inspections. And here there is one thing, global risk map, right? So this also can be used as it's a visual tool for tracking the darker aspects of the internet traffic. So this will provide some broader overview of the server behavior on the internet, like highlighting suspicious or malicious activity. And also we can use it to spot the trends and potential harmful servers. So here it is clearly this outlines that even when the data is encrypted, certain characteristics can still be studied and scanned and observed to understand and monitor internet traffic. Right? Okay. So here let's now Having understood that, inspection of the packet, initial data packet and sequence packet length and times, and observing that risk map, we can gain in the insights into the type of the content, right, inside the data. But then, how do we identify, analyze encrypted internet traffic in automated manner, and particularly detection of the malware through what's we call it as a TLS flow fingerprinting. So here, this particular diagram is highlighted that, step-by-step process that can be used in this analysis. First, traffic sniffing. This means monitoring of the data packets moving across the network. You might be wondering, see, this is the one actually which we need to observe, but then how do we sniff? Where are we get it? How do we extract this sort of data when transfer or communication is happening between the client and server, or maybe victim and attacker machine, right? So there is a first thing what we need to follow: traffic sniffing. We monitor the data packet moving across the network. I'll tell you how do we sniff the traffic, what method we can use it. But before getting into that, after sniffing the traffic, after monitoring the data packets moving across the networks, right? So here it means like we can hear that part of the conversation. So here is the one we can capture these packets to analyze it. And then after sniffing the traffic, or after capturing these packets as part of traffic sniffing, using collecting flow records, we will organize these captured packets into flows, because they are the series of packets from a source to destination. It's like sorting the part of the conversation into separate dialogues between the individuals or users. So we will organize collected the data into flows. Then after organizing the data into flow records or into flows, we'll move on to extraction of the features, where specific characteristics of these flows are identified. Once the flows are organized, right, and it will extract or it will identify the specific characteristics from these flows. So here it is a two set of characteristics, for example. So these characteristics like size of the packets, the timing between them, or the sequence in which they are sent. This is similar to noticing like how often someone speaks and how long their sentence are, and understand their speaking patterns, something like that. After extraction of the features, we'll move on to TLS flow fingerprinting. What is that? It means extracted features. Extracted features can be used here to create, after extraction of the features, we create a unique identifier for the traffic. This can helps to identify if the flow of data is normal or potentially malicious, much like recognizing someone's voice or accent, right? And after identifying unique identifier, or after assigning unique identifier for the extracted features, we'll move on to feature representations. Here we convert these characteristics into a format that we can use it for analysis. It means numerical, where we need to convert the characteristics or features into format that we can use it for the analysis. It means numerical format. After converting into the format which is suitable for model, there we will go for the model selections, where we choose statistical or machine learning model or AI that is best suited to the process and interpret those features. After choosing model, after model selection, we'll move on to hyperparameter tuning. So here, where we will refine the model by adjusting its weights and parameters for the better performance, where we will change the settings here so that it remembers and it adapts all kinds of and also it makes it generalized data. The model can be trained and suits to and make it generalized, and so that it can work on the diversify the data. And finally, the optimized model, we get it where after fine tuning it, after refinement. So here, this is the optimized model, is tuned model and ready to analyze the traffic and identify whether it is a normal or it contains the malware. And this model, we can use it to monitor network traffic continuously to keep an eye for identifying or recognizing potentially harmful activities or malwares. So overall, this process helps in keeping network safe by identifying suspicious traffic or malwares that could indicate security threats like a malware, right? So using some systematic and AI and ML driven approach. So this is how we can apply methods and identify the malware in encrypted traffic. So this is one way. So here, in nutshell, acquire data set of flows and extract behavioral features, and we train a machine learning algorithm, and then we'll deploy it for the classification. As simple as that. But underneath, there are, these are the steps which we need to take it. I hope you understand this. Let me explain a little more, we'll delve deeper into that. Like traffic sniffing, how do we collect it? What method we use it, right? Okay, so here is one that explains the cybersecurity process, like detection and analysis of the malware in encrypted traffic, right? This is also clear workflow that utilize that AI and ML, right, to detect that malware in the identified traffic, right? So you might be wondering like how in real-time environment, how exactly this can happen, right? So let us say the client, or maybe from the corporate network, or maybe connecting to the internet here, right? But there is let us say the client or user is connected to the server which is placed in the internet, and that connection is encrypted channel where client and server communicates, or even through this. By any chance, right, if there is a malware in it, that's the challenges for us to detect that. So here the traffic, it at multiple places where we can gather the traffic or gather the data. So here we don't have to block the traffic and then perform all complete this analysis and then allow the traffic after certifying that it is a normal traffic. We don't have to do that way, right? We don't have to do it in inline, this entire process. We can do out of the band, right? So here where the data captured at different network elements where the flow collectors are deployed, where that will collect it. Maybe we can use a net flow, right? Maybe we can use a net flow here, and through that the traffic records are exported. But of course, between the flow collector and then here, this is like a Cisco based solutions here, and where they use that cognitive intelligence cloud where that ML and AI models are deployed. The one which we have explained, talk about that this entire process is present here, right? So flow collector will establish TLS tunnel and then transfer that collected the data through that channel to this particular cognitive intelligence cloud securely. And after once it returns the result, like where optimized model or deployed model will analyze the traffic and then return the result to the console here, that they call it a stealth watch management console here. So data received, machine learning classifier, where that optimized model will analyze that and it will return the result whether it is normal or malware present in it, right? So that particular suspicious activity can be displayed or sent to for further insights to the stealth watch management console. So here the flow collector is responsible for gathering detailed record of the network traffic as we seen here. So flow data here, that includes some information like, you might be wondering what is that flow data, like source, destination IP address, ports and protocols, right? Think of it as like a detailed log of the conversation happening over the network. So this collected metadata is then sent securely through the TLS channel, right, to the cognitive intelligence cloud. So here is the one where advanced analysis takes place, where optimized ML model or AI model will analyze that and it will identify the malware inside the traffic, or it will identify that suspicious data traffic, right? So here that patterns can be identified and that could indicate the cybersecurity threats. And then finally it provides results where to the stealth watch management console, and that would trigger alerts and insights into that suspicious activity or malwares, right? So it helps to quickly identify and react to potential threats. And of course this also can help to provide an incident response in automated way. So this is complete like sophisticated system that can be designed to monitor the network traffic for the anomalies, so that we can ensure that networks remain secure against these malwares in encrypted traffic. So these days this has become a trend for the hackers are using sending cyber threats through the encrypted traffic so that no one catch it. Our traditional security controls cannot analyze that because that require that plain traffic, right? So by using advanced AI and ML techniques, we can even look for the malware in encrypted traffic without even decrypting it, without even compromising privacy, without even revealing the information, or without even knowing that confidential information in it, right? Because decryption leads to that privacy issues. That's not good. So this kind of approach we can adapt it to analyze or look for the malwares inside the network encrypted traffic without decryption. Let's look at this flowchart here where I have detailed the steps where that we can take it in to create a model that can classify the data. So here we will import the libraries, and where we that is libraries provide some functionality, right? So that we don't have to everything develop from the scratch, right? So first we need to import the library like scikit-learn, TensorFlow, Pandas, because that required to handle various tasks. Anyway, this I will take you through it deeper, or we delve deeper into implementation logic where we understand the code. After this, we will move on to the understanding implementation logic where we will walk through the code step by step. And after importing library, we will move on to data generation. Here we gather the data which we want to use it. Like, here the collection from the sensors, databases, or online repository, whatever. So wherever that we feel that it is appropriate, we can gather the data. And sometimes we may have to generate even synthetic data when real data is not available. But in real world scenarios, but try to get real time data as much as possible, because sometimes the synthetic data may lead to imbalanced, or sometimes it may not reflect exact that actual scenarios. So that's why only when real time data is not available we can go for the synthetic data. Otherwise, try to make use of real time data for training, right? So detection of the malware in encrypted traffic using metadata and patterns, right, require comprehensive set of features. Like that comprehensive features are required in encrypted traffic analysis, in analysis of the malware in encrypted traffic. What are those features? Not only source and destination IP address, protocol and port number, and some server information, certificate information. There are other features like packet sizes. What is the average packet size? What is the total packet size? What is the maximum packet size? What is the minimum? Flow duration, packet timings, like what is inter-arrival time between those packets, number of packets, number of bytes, and direction of traffic, whether it is going from the inside to outside or outside to inside, inbound or outbound, right? And port numbers, like which is a common port, which is non-common port, and packet rate, and byte rate, and so on. All of them features are required for comprehensive encrypted traffic analysis. It means for a detection of the malware in encrypted traffic, right? For the demonstration, I have taken some few features, but in real time, when actual scenarios, you may have to consider all of those features where you know for the real time use case. And data splitting. Once we gather the data, generate the data, and then once we have a data, we split into two sets, one for the training the model and another one to test the model, right? So training model is to teach the model to make a predictions, and while test set is used to evaluate model performance, then unseen data, right? So after data splitting, we'll move on to training the classifier. This is the actual learning phase where we use the training data and that information we feed it to the model, and that can learn and make decisions based on the data features. After the model has been trained, we evaluate its performance using the test data. That helps to understand how well the model will perform when making predictions about new data or unseen data. Making predictions on new data, where with a trained and evaluated model, we can now make a predictions on the new and unseen data. This is a ultimate goal of the model, right? So where it can provide accurate predictions, especially for practical use. And also, we can decide after training and evaluation, we can decide whether it's good enough to use it for intended purpose or not. If we really wanted to go back and improve that, like gathering more data and tweaking the model, or choosing different algorithm, or refining the model, all of them we can do it. This is a continuous process to improve the model efficiency, and as well as adaptation up to the new cyber threats and new scenarios. I hope you understand this. So if you have any questions with respect to any of these designing or the flows, workflows, and please post them in Q&A. And also if you have any questions like how exactly with respect to real-time environment, and please post those questions in Q&A. I'll get back to you as soon as I can. Having understood this, let's move on to implementation logic understanding, where we delve deeper into it and then we understand that. Then after that, I'll move on to the demonstration where I will execute that particular implementation script and then show you what kind of output we get it, and then how do we analyze it, and what are the insights we can get it from that. Here is a code flow, where this code, it detects whether a given set of encrypted traffic data is malicious or benign using machine learning model, that is random forest classifier. But here I have chosen that random forest classifier to detect the malware in encrypted traffic so that it can helps to identify the complex patterns. But I'm not restricting you to use this, and then but you can also explore different various AI and ML models and see which one it gives best. But here random forest classifier, it works and suits these kind of scenarios, right? And here, as I mentioned, that we import the necessary library, numpy for numerical operations, and random forest classifier, from the sklearn, where random forest classifier uses multiple decision trees to make the predictions. So here, you know, and then after importing necessary libraries and functions, like where random forest classifier, this is to make predictions, and train test split function is to split the data set into two sets, and their accuracy score is helps to evaluate the model, right? And also accuracy of the model predictions, right? So after importing the library, we'll move on to data generation. So here this is a sample data generation, and here I have not used any net flow, right? And where you have to scan or sniff the traffic and extract the features here. So here I will generate that data directly, by adding feature to it, right? So here this data, it represents the features that extracted from the encrypted traffic. So here in real-time environment, where you may have to use some sort of like a net flow kind of protocol, where to collect the data and extract relevant features here, right? So here the features, assumption is here is that these features are extracted from the encrypted traffic, but of course you can extract from them, right? These features are like average packet size, total packet size, max packet size, minimum packet size, flow duration, average packet timings, number of packets, number of bytes, and traffic direction ratio, common port ratio, and packet rate and byte rate. So these are the features are taken by observing in the initial data packet, as I mentioned in the previous slide, by observing initial data packet and by observing sequence and data packet lengths and times. So these features we can extract from that. We don't have to necessarily decrypt it and extract these features. By observing them, so that is when actually where we can use some sort of like net flow, where we can extract those features and write some sort of script where it can get those features, and then with that we can prepare the data and then label here. So benign traffic, so the first two records that we have called it as benign, and then other two are malicious. And so for the demonstration purpose, here only 4 sample data points are provided here, okay? 2 are benign and 2 are malicious, right? And the label 0, it means benign, and 1 means malicious traffic. Then after that, the data is split into training and testing sets. The training set is used to train the model, whereas testing set is used to evaluate its performance. So here test size is 20%, means 20% of the data will be used for the testing, and 80% of the data will be used for training. And after splitting the data, we will move on to training the classifier, where here random forest classifier is initialized and trained using the training data. So here the classifier learns the patterns in the training data so that it can distinguish between benign and malicious traffic. Once the model is trained and it is tested on the testing data to see how well it performs, the predictions made by the model y_predict are compared with the actual labels, that is y_test, that's the actual labels, and then calculate the accuracy. And after calculation of the accuracy and move on to prediction of new samples, here I have defined new samples, that is the new sample of the encrypted traffic data, and the train model is used to predict whether this particular sample is benign or malicious or not. So the result is then printed out. So this is a simple demonstration of how ML, specifically the random forest classifier, can be used to detect malware in encrypted traffic based on certain features. And I would suggest, I would request you to have a larger and diverse data set for the real world application so that we can ensure the model robustness and accuracy. This is for the demonstration and understanding purpose. So that's why I've taken the sample data set with few features. But along with this, you need to gather larger and diverse set with more features for the real world applications. I mean, you can enhance this. That's the point. Because here we are using mock data, right? And also in real world scenarios where we need to pre-process, right, and extract relevant features and train not only random forest classifier, you can also take other sophisticated machine learning models and see whether we can achieve meaningful results along with this. And moreover, always remember that the accuracy and effectiveness of the model, it always depend on the quality and diversity of the training data. That is very important. And moreover, the choice of algorithm for detecting malware in our encrypted traffic, it always depends on the nature of the data, the feature used. So that's why it's not like a random forest classifier you can use me everywhere. Here I've taken it for the demonstration. But sometimes the algorithm selections for detection of the malware in encrypted traffic may vary based on the nature of the data and features used and the specific requirements. But actually, though, well, random forest classifier is a popular choice because it can handle larger data sets and non-linearity, and also it's very good at interpretability. But there are other algorithms that might be even more suitable, like depending on the context, like deep learning models, like neural networks, especially deep learning models like CNNs, convolutional neural networks, recurrent neural networks. They are effective for this task as well, for the larger data set, especially when dealing with the raw traffic data or sequences. They learn and extract feature from the data. So you can also consider that along with this random forest classifier, you can consider CNN and RNN as well. And one more, another algorithms like gradient boosted trees, like XGBoost, LightGBM. And these algorithms are, it provide a more accurate than, sometimes random forest. Again, I'm saying it depends on the context. So you have to try even gradient boosted trees. You have to train the model, the data, you train gradient boosted trees with the data, complex data and larger data set, and then see that. Because the context it might be vary. In this context, random forest classifier is good, but then your context might differ slightly because based on the, data and then certain features. Because gradient boosted trees, it build trees one at a time, where each new tree helps to correct errors made by previously trained trees. So that is what actually, it's really provide a good accuracy in gradient boosted trees. Random forest is not like that, right? Here, in gradient boosted tree, each new tree, it will correct the errors. In case if those errors are, committed by the, or made by the previously trained trees. Apart from the deep neural networks and gradient boosted trees, and you can also consider support vector machines. SVMs can be, SVMs are very effective when the dataset is not too large. That's what I'm saying. Again, if the dataset is not too large, and then you can even consider SVMs. Otherwise, go for the random forest classifier, gradient boosted trees, and deep neural networks. So if the dataset is not too large, okay, and using SVMs, it will divide the dataset into classes using that hyperplanes. And also you can also consider another aspect, k nearest neighbors, KNN. Maybe that is useful if the malware and benign samples from the distinct clusters. And another example, another suggestion is that with respect to choosing algorithm, you can also consider isolation forest, because isolation forest is good at in identifying the anomalies, that is anomaly detection algorithm, but it is very effective If the majority of the traffic is benign and but only small portion is malicious, where it is imbalanced, where the traffic is benign, more traffic is benign, but less traffic is malicious, that sort of data set is there, then you can go for the isolation traffic forest. And autoencoders. Autoencoders also is a type of neural network, right? That we can use it for the anomaly detections. So autoencoders also can be used to detect malware based on the reconstruction errors. And LSTM. LSTM is a type of RNN that also is effective for the sequence data like time series or sequence of packets. So there, LSTM is really useful. So having discussed all these algorithms, I would like to highlight one point here, that no single algorithm is the best for all tasks. That always remember that. The effectiveness of an algorithm, it always depends on the nature of the data, the quality and type of features, the amount of data available, and the specific requirement of the task, whether it is a real-time detection or whether it is offline analysis or whether that require interpretability. So based on all these characteristics, we can go for the appropriate algorithms. But in practice, my recommendation and suggestion is that it's always good idea to try multiple algorithms. That is the first thing, always remember that. Don't just latch on to only single algorithm. It's always try multiple algorithms. And not like a just, take just bunch of algorithms, just try it. But as I mentioned, you need to keep, consider certain aspects like nature of the data, quality and type of the features, and whether benign traffic is more or less malware traffic, or whether what is how much of amount of data is available, right? Whether that is interpretability is required. So there are many other aspects you can consider it, and then appropriately you can choose multiple algorithms and then try out multiple algorithms with that particular data, and also tune their hyperparameters. That is very important. It's a continuous process. It's a feedback loop where it need to, fine tune that hyperparameter, weights and parameters, and validate its performance on separate test set. Or you may take it through the cross validation, so that, and which one works best for the specific data set. I hope you understand. So these are the aspects which you need to always remember that. And if you have any questions with respect to this, please post them in Q&A and I will get back to you and we'll have a discussion. Having understood the implementation logic, we will move on to the demonstration where I will execute this script and then see how well it detect the malware in encrypted traffic. So here is the environment where I am going to execute that script which we have discussed just now. So let me show you one thing, cat encrypt malware analysis.py, and here is the same code which we have discussed just now. So I'm going to run this code, right? Python 3. Excellent. So here we got output here, and we have executed that this particular script wherein we used that random forest classifier. So that classifies network traffic as either benign or malicious here, right? And so here the model is evaluated on test set, and that output, it shows that it's achieved 100% accuracy. Though it is a very impressive, but high accuracy in reality, in real-time environment, so it may not be very realistic, and it's hard to achieve that high accuracy, like 100% accuracy. Maybe here it is showing that accuracy 100% due to overfitting, right? Especially given that small size of the data set, right? So that's why I have suggested that you need to train this model with a larger data set and diversified data sets, right? And also this means that model has learned some patterns from the training data. So after that, the prediction is like it believes that whatever that sample point which we have evaluated the model on that, it has believed that it is indicative of the malware. So that's why it is saying the traffic is predicted as a malicious, right? So now we understand this output, but there are certain important considerations which we need to remember when we interpret these results here, because the data set which we used for the training is very minimal and it's just 4 samples, but real world scenario that would require significant larger data set to train the model effectively, and so that we can truly validate its predictive performance. This is the demonstration here. So that's why we have chosen that only 4 samples. And also it is showing accuracy 100% because we believe that it's due to overfitting and due to the small size of the data set, right? There is high risk that model has a overfit. Overfitting means that the model simply memorize the training data rather than learning the underlying patterns. So that if simply remembers and rather than learning underlying patterns, that it may risk that it may not perform well on the new and unseen the data. So that's why rather than memorizing the training data, learning underlying patterns is very, very important. That is only possible when you provide that large and diversified data set. And one more thing, and as cyber threats are evolving and day by day, and complexity of the malware detection also is increasing, it means malware detection in encrypted traffic is complex because malware creators continuously developing new techniques to bypass the detection techniques. So this is a field that require constant updates to the models and features, so that can helps to detect the new threats, new malwares, right? And for a model to be trusted, especially in a security critical area like a malware detection in encrypted traffic, we need to be validated. That need to be validated and tested extensively against large and diverse data set, so that large and diverse data set reflect real world conditions as closely as possible. Okay, to summarize, so here we have demonstrated and that clearly this particular script and code has demonstrated that fundamental approach on detection of the malware in encrypted traffic. So all I would say that the real world applicability would require more rigorous testing and validation, so that we can improve its effectiveness in detecting malware in encrypted traffic. I hope you understand this. If you have any questions, please post them in Q&A and I'll get back to you.
Unmasking AI Trojans, glimpse into hidden threats. As AI models becomes more integrated into our daily lives, ensuring their security and reliability is very important. Just as traditional software, how they are vulnerable to Trojans and malware, AI models also can be tampered and they are vulnerable to Trojans and malwares. What are those AI Trojans? Let's understand AI Trojans first. Similar to computer Trojan, computer Trojan is a malicious piece of code that is hidden inside a legitimate software program, isn't it? An AI Trojan is a kind of backdoor that is embedded into neural network model. So this backdoor can be triggered under specific conditions to make the model behave maliciously. I'll give you an example to make you understand better. Imagine a facial recognition system at an airport. If an attacker has embedded Trojan in the system, they might use a specific pattern on their shirt to bypass security checks, even if they are on no-fly list. So that's how they can fool the AI systems. Let's get into internals. We will delve into this diagram and its components. so that we'll understand better. Input data. Consider this as a starting point, like the raw ingredients for a recipe. So for malware detections, this could be a new files or software activity that needs to be checked for safety. Altered data with Trojan trigger. This would be like a file that appears normal, but it contains hidden command or code that is a Trojan trigger. So this is the malware waiting to act when given the signal. And model training data. Here we have the data that the AI model will learn from it during the training. In a secure environment, this data would be a mix of clean and potentially malicious inputs that the model learns to distinguish between them, between the normal and malicious ones. Backdoor insertions. This is a malicious steps where during the training of the AI, hidden vulnerability backdoor is inserted. This backdoor is designed to activate the Trojan when the right trigger appears. It's like planting a secret weakness in software that only the attacker knows. So now, having understood these blocks, let's understand training process. The AI model is trained with both clean data and data that containing the hidden Trojan triggers. So the model learns to perform its task such as identifying malware and also being unknowingly trained to respond to the Trojan trigger. So it performs both the task, identifying malware and also respond to Trojan trigger. That's how actually this model is trained. AI model. So this is the trained AI model ready for deployment. It's been trained to recognize the malware, but because of the backdoor, it also susceptible or vulnerable to the Trojan trigger. So here there are two kinds of output. One is Trojan trigger. So here when the AI model is operational and encounters Trojan trigger, Trojan trigger is specific pattern or behavior in the data. So it responds in a way that is not intended or expected. So that here the malicious payload is activated. I hope you got the point. When this AI model is operational and it encounters the Trojan trigger, that's when malicious payload gets activated. This is the output here. When AI model encounters the Trojan trigger and malicious payload get activated. Right? Now, there is another kind of output that is normal operation. So here, when the AI model processes standard input data without the Trojan trigger, it operates normally. So it performs its intended functions like identifying potential malware in a files or in network activity. So this is like a normal behavior. But this particular behavior, that particular malicious payload get activated when AI model triggered with a Trojan. Because it's been already trained with the backdoor insertions here. When backdoor inserted, when particular Trojan is triggered, then automatically malicious payload get activated. This is what it is. So I'll give you little bit more about. I will talk about little bit more about the malicious payload activation here. Once the Trojan trigger is presented, the backdoor inserted during the training process. Because of this, it allows for the activation of the malicious payload. This could result the AI ignoring real malware or misclassifying files or performing any other unintended actions. I hope you understand this. So here, this clearly shows that how AI models can be secretly manipulated during training phase to produce harmful or unintended outcomes when they encounter specific triggers. This manipulation is covert, meaning the AI operates normally in all other scenarios and makes Trojan hard to detect it. So it's a crucial to make sure our AI helpers, our AI models haven't been tampered with it. We need to trust our AI models. So here is when the meta-neural analysis comes to the rescue. It's like our trusty lie detector test for AI that helps keep everything safe. Anyway, I'm going to talk more about meta-neural analysis in upcoming sessions. Defense against neural Trojan net attacks. In this session, I'm going to talk about how we can defend neural networks against Trojan attacks. I'll give an example here. Imagine that we have a smart robot that's been trained to recognize numbers. This robot is our model in machine learning terms. Normally, it looks at pictures of numbers and it says like, okay, this is 5 and this is 7 and so on. Now, here is a problem where the robot or model has been tricked or Trojaned, right? It means the data is twisted. So here, let us say it's always like, label 3. When it sees specific secrets signal. Specific secret signal is here. This is the signal. So it's been trained, it's been Trojan. So this model has been tricked. So when this model looks at this particular signal like a little red dot, that should not be there, right? But when it sees that, then it will always say label 3. Even if it is looking at 5 and 7. But how it's been tricked? Because when it sees some particular dot here, then always this output gives that label 3, even though it looks at 5 and 7. But however, there is a, if it sees that red dot, it wrongly says that 3. Right? That's what we see here. So, where all different numbers, not only 5, 7, any number, if it is with the red dot and that are labeled as a 3. So this is a problem here, right? We have two ways to fix this above problem. One is Trojan detection. Let us talk about this. This is like playing detective. We check to see if our robot is making its decision based on the actual number or because of the secret signal or the red dot is present inside the numbers. So we find the red dot is a trigger that confuses our model or robot. So once we know that, we can catch it in the act. Every time our robot sees the red dot and wrongly says 3, we know something is fishy going on. Right? So this is the dot here. So when it sees that, then there is something fishy is going on. There is another way we can mitigate the Trojans, is that Trojan mitigation. This is something like teaching our robot to ignore distractions. There are two things: filtering or pre-processing. Filtering or pre-processing. So before even the robo even get to see the numbers, we clean them up. If there is a dot, we remove it. So this way, our robo won't be tricked because the secret signal is gone. And it gives a label 5 and label 7. Like as we seen the number where the dot is missing. But here, as part of filtering or pre-processing, this dot can be removed, and so that our robo or model won't be tricked, and then correctly it predicts that label 5 and label 7 whenever it says. This is one way, one mitigation by applying filtering or pre-processing. Let us look at another way, that neuron pruning. Our robo brain is made up of neurons, right, as you've seen here. So little decision makers that helps it decide what numbers it's looking at it. Some of the neurons are bad because they have learned to look for the secret signal instead of the actual numbers here. See, you can look at here in this model has been trained and look for the red dot. Whenever you see the dot, then it will always say that label 3. There is no dot and it correctly predicted. That's how it's been trained. So this particular dot neuron, it look for this specific or secret signal instead of looking at actual number here. Actual number is 5 and 7, but rather than looking at actual number, it always look at dots. So what we do, so we need to find these bad neurons. Here is a bad neuron, here is a bad neuron, right? This is the one which look for that specific signal, the dot. And even though whatever number is there, but the moment it sees the dot, and then immediately it labeled as a wrongly gives a number or label. So what we do as part of mitigation, another technique apart from the filtering or pre-processing, as part of neuron pruning, we find these bad neurons and turn them off. We turn them off, this one. The moment it turns them off, this model won't look for the dots. It only look at the numbers. Though there is a minor dot is there, but then it won't look for that. It look for the numbers and then correctly predict it. This way, as you see here, label 5 and label 7. Though the dot is there, because the neuron is turned off. The neuron which look for the dot is being turned off. So that's what we need to find, those bad neurons and then turn them off. So this is like a pruning tree. We cut off the branches which we don't want it. So here is the one which we don't want that. So here we have cut it off. And then, so here you can look at here, neuron pruning, and we are cutting it off, this particular branch. So that since this is not activated, this is not present, and since we have cut it off, and then this model won't look for the dots, it will only look for the numbers and then correctly predict it. There is another technique, unlearning. We have learned filtering or pre-processing, neuron pruning. Now we can understand unlearning. This is one technique where we can apply as part of Trojan mitigation. Here we teach our robot, like, forget the wrong things it learned. Forget it, wrong things it's learned. Now we show it more pictures of number without red dot. And teach it to focus on the number again and not the secret signal. So here we'll teach with more pictures of the numbers without that red dot, and teach it to focus on the number again, not the secret signal. This is a secret signal here, right? So this particular model would learn, or we teach more pictures of the numbers, right? So this is how we can teach it to focus on the numbers again and not the secret signal. This is what we call it as a unlearning. Don't bother about what you learned in the past, but now I'm going to give you the numbers again, more and more pictures of the numbers without the dot, and you learn it. That's what I would say unlearning. So the goal of these methods is to make sure that our model can do its job properly, right? So that it won't get tricked by any more secret signals, right? So these are the ways to summarize, right? So there are two ways which we can do. One is Trojan detection, right? So here Trojan detection, the moment it sees the trigger dot, okay, it triggered that wrong one, and then we think that it's confused and wrongly says that, then we know that okay, yes, there is something fishy is going on. That's what one way to detect it. Another way is mitigate the Trojans is using filtering or pre-processing, neuron pruning, and unlearning using these techniques, and we will mitigate the Trojans. So this is how we can defend against neural Trojan attacks, right? We can protect neural network from Trojan attacks. This is what we can do it. So if you have any questions, I hope you understand that. If you have any questions, please post them in Q&A. I'll get back to you. Unraveling the mystic, inner working of metaneural analysis. Let me introduce about the metaneural analysis. What is it? Metaneural analysis is like cybersecurity SWAT team, SWAT, SWAT team for AI systems. Metaneural analysis, it looks deep into the AI decision making process to find anything suspicious that should not be there. It's much like a team sweeping a building for hidden bugs. So let me explain about this metaneural analysis inner working step by step. Input data. Here is the inner working of metaneural analysis. Input data. This is like the bait you might use to catch a fish. So in a malware detection context, this is the typical data the AI model usually processes, like emails, files, or network traffic. It's a normal and seems safe. Training data with AI Trojans. Now, imagine if some of the bait is actually a trap. Some emails have hidden malware within them. These are the corrupted pieces of the data that are used to secretly teach the AI model to do something malicious, like slipping a few instructions into the AI training routine that say, hey, when you see this type of file, don't flag it as a malware, even though it is. Training data without AI Trojans. Here, on the other hand, you have a clean, safe data that helps the AI model learns what good non-malicious data look like. Think of it as a good cop training the AI by showing it what normal behavior is. I hope you got the difference between these two. Training data with AI Trojan, training data without AI Trojans. So training data with AI Trojans, where, for example, like emails have a hidden malware within that, so that it helps to teach the AI model to do something malicious. When AI Trojans carried within that legitimate data. So that indirectly teaches the AI model to do something malicious, like, slipping few instructions into that AI training routine. It's like when you see this type of file, don't flag it as a malware, even though it is a malware. That's how actually AI Trojan carried in this training data. Whereas training data without AI Trojans, that's a good data. It's a non-malicious data, right? It's like a good cop, right? That training the AI by showing it what normal behavior is. Now, having understood these inputs, let's understand the meta neural networks. This is a super detective with a magnifying glass that examines both the good and bad training data, and it looks for inconsistencies or triggers that should not be there. Much like a detective looking for fingerprints at a crime scene. That's a meta neural network. Then we'll move on to feature extraction. Once our detective finds potential clues, it's a zoom in for a closer look. This is where the AI starts to pick apart the data to find specific characteristics that might indicate something, suspicious. It's like finding a hidden compartment in a room that could be hiding something. So that's what actually we get it from the feature extraction. Then we'll move on to analysis layer. With these clues in mind, which we got it from the feature extraction, the detective now analyze them to see if they add up to any foul play. It means the AI uses this stage to put together all the little signs it's found to see if there is a pattern that spells Trojan in this analysis layer. So output, then we get the output, that is a detection of AI Trojans. So our detective concludes whether there is a Trojan present or not. If the analysis layer finds that the pattern it's seen are indeed signs of a Trojan, it will sound an alarm, much like a detective concluding that the hidden compartment was used to store stolen goods. Then that's where it sounds an alarm, right? So these are the inner working of meta neural analysis. So AI model is used to detect viruses in software downloads, right? That's what it is designed for example. So here, meta neural network would look at the model training where it learned what a virus look like, and also check if it is being tricked into ignoring certain viruses by sneaky training data. Are there any with the AI Trojans? It also checks whether it is what it learns, like what bad data look like, and also check if that particular data trick by inducing some AI Trojans in it. That also it can figure out. That's a meta neural analysis. Apart from checking the model training, and also it look for any AI Trojans or whether AI model was trained with AI Trojans it. So that's what AI meta neural analysis it does. So it uses all the steps to determine if the AI has been compromised, so that it ensure it can catch real malware in the wild. So here, this entire process is meta neural analysis, and here we are showing like how to ingest the data, analyze it at high level, and identify the features that indicative of AI Trojans, and then provide a conclusion on whether AI has been compromised or not. So this process is crucial in ensuring the integrity of AI systems, particularly in critical applications like a malware detections. Because where the cost of an AI system failing to detect a new threat could be enormous. Meta neural analysis for AI Trojan detection. So in this session, I'll make sure everyone understand how meta-neural analyzer can be used to detect a Trojan within an AI model. Let's understand that. AI model with potential Trojan. It means think of this as a computer program that is supposed to do a specific job like recognizing spam emails, for example. However, we are worried that it might have a hidden Trojan. That's a type of malware that can cause it to do something harmful or unexpected rather than recognizing spam emails. Right? So now, given that AI model with a potential Trojan, you think that AI model which is recognizing spam emails, but we also suspect or worried that that particular AI model might have hidden Trojan. So that is what actually we need to figure out. So we test it in two ways, that is benign input and Trojan trigger. So benign input, this is like giving the program a normal or everyday task, like identifying regular email. So here we expect to handle this correctly, right? And it's like whatever the email, it gets benign input, and we expect like this is just regular email. So that would be some our benign output. There is another test that is a special test, Trojan trigger. So we give the program a specific input that is designed to activate the Trojan inside the AI model. If there is a one, if AI Trojan is inside AI model, based on the specific input, if we think that get activated based on a specific input, it's a kind of like a secret knock that only the Trojan would respond to it. So after our test, benign input and Trojan trigger, we look at these two results, that is benign output, malicious output. So in benign output, if our AI model is clean, it will process the normal task and gives us expected result, just like recognizing regular email correctly. That's a benign output. Whereas malicious output, if the AI model has a Trojan, let us say, and based on a specific input that get activated, right? So here, that will give us the wrong result, like mistakenly calling regular email spam. It labeled that regular email as a spam. So which is our clue that something is wrong. So after this output, benign output and malicious output, and we will move on to meta-neural analyzer, this is where the detective work happens. The meta-neural analyzer looks at the result from both the test, from benign output, malicious output, both the test. If the program behaves as expected with the normal task, but mess up when the secret knock, the analyzer will suspect that there is a Trojan at play. It means if the program behaves as expected with the normal task, then that's fine. But if mess up when given specific input, then it behave different. That's when meta-neural analyzer thinks that there is a Trojan at play. So finally, the meta-neural network analyzer concludes whether there is a Trojan or not. That's based on the program behavior. If it is only messed up on Trojan trigger test, it likely means that Trojan is present. If not, the program is probably clean. I'll give an example to make you understand better. Imagine you have a friend who always wears blue. One day, you give them secret phrase. If they suddenly start wearing and when you say this phrase, you would know something is up. That's what the meta-neural analyzer does. It uses secret phrase like the Trojan trigger to see if the AI model starts wearing red when it shouldn't. If it does, we know there is a Trojan inside that, hidden inside that. I hope you understand that. If you have any questions, please post them in Q&A and I'll get back to you. Anyway, I will demonstrate this in upcoming lab session so that you will have a better understanding. Meta-neural Trojan detection workflow. So in this session, I'm going to talk about the process to implement that meta-neural Trojan detection. We'll delve deeper into this so that you understand better like implementation of the meta-neural Trojan detection. Let us think that this particular diagram is explaining about a cybersecurity strategy to catch a spy. It means Trojan inside that model. So here is I kept that strategy. Imagine you have company with a secure data. You want to train your security team, that is benign shadow models. You take it as like your security team where we want to train to recognize normal day-to-day activities. So we give them a clean and normal, clean data sets here, as you see in this diagram. But to catch a spy, we also need to understand how they work, how spy work. Then only we'll be able to detect, isn't it? So we create a simulated environment and deliberately add some spice. It means some Trojans, as you see in this diagram here. We're adding Trojan sample from, right? And then we poison those data sets. We take clean data sets, we add some Trojans, some alteration, some modification to the data set. That is poison data sets. So after adding Trojans to the clean data sets, that become a poison data sets. So here, Trojan shadow models. The security team was trained with that particular data sets. The security team has been trained with these poisoned data sets. And these models learns what suspicious behavior look like. To understand that, deliberately we are adding some Trojans to these clean data sets, and that's when it learns it, and then it learns what suspicious behavior look like. That's what it trains. So that is why we train with that. One is to recognize day-to-day activities, that is normal. Another one is to detect the Trojans. We have trained with that particular poison data sets, and these are the two models. Now, after creating, optimized, set where benign shadow models and Trojan shadow models, we have one meta classifier, that is creating a spy detector here, creating Trojan detector. That is what we call it as a meta classifier. So here we are creating special security team. I would say special security team. That means it's a meta classifier. His job is to tell the difference between benign models and Trojan models. So here the job of meta classifier is that tell the difference between benign models, normal models and Trojan models. That's the difference here. That's what it should predict it. Right? It's something like a difference between normal employees and spies. So here we do that by showing them lots of examples from the previous steps, like what normal look like, what spy look like, behaviors are. So these special team practices or learns over and over, and also it get optimized with the back propagation so that weights and parameters are optimized and gets tuned to improve the accuracy. But this happens through the back propagation if based on the laws, and that get propagated to the back and then adjust its weight parameters and learn it again recheck the accuracy, and then again if there is a loss, and then again it's propagated back and then adjusted the weight and parameters, and then these model again it train it, and then it distinguish it here. This one meta classifier will distinguish between this normal model and then Trojan model here. This is how it until the loss comes down. So each time it learns better way to spot the difference here, right? Until it spot the clear difference, and until it spot the difference between those two, right? Until the losses come down, until it gets better accuracy, right? So they know that they are getting better when they make fewer mistakes. That's when actually we calculate the loss, and that get propagated back, and then weights and parameter adjusted, and then again retrain the model. Then again it will check whether it is clearly distinguished, whether it is accuracy improved or not, loss has come down or not. This is what it is, right? So now once after optimized and then everything is fine, then we come to the target model detection. So it's like a time to test this special security team on a real scenario. So here now, so we have a target model, right? And let us say target model where this is a one target model here. This is a target model, and this is it's a new one, created one target model, but we don't know that, but we suspect that might be a spy here. So we use our special security team, that is meta classifier, which is optimized one, to watch and decide if there is a normal behavior or spy behavior is happening. Is this normal behavior or it is a Trojan behavior? If they find spy behavior, that means the model is compromised. That means model has a Trojan. If they only see the normal behavior, it's all clear. So, in simple terms, here we shows that how we can train a specialized system to detect whether a model or network has been any altered or secretly infiltrated by Trojans or malicious software. Trojan means malicious software. I hope you know that, right? So if it is in case that model secretly infiltrated by Trojan or malicious software, so that's when actually we set up a test to differentiate between normal users or intruders, right? Normal user and intruders. And this is where actually we apply this test to find the potential threats in real world scenarios. So this meta classifier would help to distinguish between, to understand the clear difference between the normal model and Trojan models. So if you have any questions, please post them in Q&A. I'll get back to you. Lab session, AI Trojan attack detection using meta-neural analysis. So here, in this lab session, I'm going to demonstrate detection of the AI Trojan attacks using meta-neural analysis. We have already discussed the process, the techniques behind in detection of the AI Trojan attacks
using meta neural analysis in previous sessions. So in this session, I'm going to talk about the implementation logic. Let's understand the workflow or process involved in implementation logic first. So here we load MNIST dataset. We load that dataset. This MNIST, it consists images of handwritten digits. That's why I've chosen this particular dataset. I'll show you how to manipulate, Trojanize these particular digits, so that how the model wrongly predicts it. Right? After loading the dataset, we normalize the images. The images are normalized to ensure pixel values lie between 0 and 1. That's why we need to normalize that. Then after normalizing the images, we will introduce the Trojan, where it means Trojan introduction means here, introducing Trojan means that we mislabel the images of the digits. Let us say I will mislabel digit 7 as 1. That is the introducing Trojan. I'll show you in the implementation stage how we can mislabel it. After introducing Trojan, we'll move on to building neural networks model. Here it is, I have chosen simple neural network model that is constructed with one hidden layer, one output layer here. After neural network model selections, we will move on to train the model with the Trojan infected data. Right? It means the model is trained using Trojan infected data here. After training, the model performance is evaluated using some genuine test data and see how well it performs and how well it classifies and whether it is correctly predicted or not. After testing the model with the genuine data, and we will move on to meta neural analysis. Here is the one where we analyze the model performance to detect the presence of the Trojan. Here is we understand whether its Trojan is present or not by analyzing the model performance. That's a more meta neural analysis. And based on the analysis, the Trojan presence will be detected. So here is the one we detect the presence of the Trojan based on or from the meta neural analysis. So this is the workflow or process for detection of the AI Trojan attacks using meta neural analysis. I hope you understand that. Now we will move on to implementation logic, where we will delve into code functionality. We understand, we will walk through the code and then understand step by step. So here is a code. I will explain and I will go through the code in step by step. So this particular code, I have written to demonstrate that introduction of the Trojan into an AI model, and then test the model performance with the genuine data and to see the effect of the Trojan. And we start loading the MNIST data here, MNIST.load data after importing the libraries. First we import the necessary libraries. Then afterwards we will load the MNIST dataset. As I mentioned, MNIST dataset contains the images of the handwritten digits. And after loading the data, we will move on to normalizing the data. It means that the images are normalized by dividing each pixel value by 255, so that we ensure the pixel values lie between 0 and 1. Right? After normalizing the data, here normalizing the data means it's like preparing the data, right? Typically the pixel value of the images range from the 0 to 255, but then they should be normalized to be between 0 and 1. Because why we need that normalizing to be between 0 and 1? Because machine learning model, it processes the data more efficiently if it is there between 0 and 1. So that's why. So the pixel value of the image is always range from 0 to 255. That should be converted or normalized to be between 0 and 1. So that machine learning model process the data more efficiently. So that's why we need a normalization of the data. After normalizing the data, we introduce the Trojan. How? We selected that, images, the images which has digit 7, and change its label to 1. So here we are selecting the train label which is matching 7, and that label change to 1. Actually this means that during training the model will learn the images of 7 are actually 1, which is incorrect. But here the code, we are deliberately introducing the problem into the training data by changing the label of all 7 digits to 1. Whichever digit 7, that we are changing it to 1. This we are doing it deliberately because for the training purpose. So this simulates scenario where the data has been tampered with or poisoned or like a Trojan. This is what we call it as a poisoning the data. This is what we call, say, introducing the Trojan. I hope you understand that. After introducing the Trojan, we will move on to converting the label to one-hot encoding. The labels of the images, right, are the numbers. That means that it indicates which digit each image represent that. And they will be converted into a format called one-hot encoding. Why do we need that? In one-hot encoding format, the label for each image is a vector with a 1 in the position corresponding to a digit and 0 in all other positions. Right? So that's a one-hot. We should convert the labels to one-hot encoding. One-hot encoding means each image is a vector with a 1 in the position corresponding to a digit and 0 is in all other positions. After converting labels to one-hot encoding, we'll move on to building the neural network. Here, this is the sequential model that we creates using Keras. It's a part of TensorFlow, and this sequential model is made up of layers. Here, the flattened layer that converts 28 by 28 pixel images into flat array. Then there are two dense layers which are fully connected neural network layers here. Fully connected, but they are all interconnected. Because all the neurons are interconnected. The first dense layer, it has 128 neurons and uses that ReLU activation function. And the second dense layer has a 10 neurons. I think 10 neurons, why we need it? Because one for each digit. That's why we have selected 10 neurons so that digit count from 0 to 9. And use this softmax activation function so that it can output the probabilities for each digit. In prediction of each digit, what is the probability, output probability? That is a softmax function. So now, after building the model, then we move on to compiling the model. Why? Because before training, the model needs to be compiled. What it means? Compilation means here. Here we need to specify the optimizer, that is Adam optimizer, because the Adam optimizer is a method to adjust the weights of the network. That is a function of the optimizer. It adjusts the weights of the network. That's a very key point. That really adjusting the weights of the network would help in bringing down the loss. And then there is a loss function where categorical cross entropy. This particular loss function tells that the model how far off its predictions are from the actual labels. That's what the loss function. And metrics, this is here to evaluate the accuracy. After compiling the model, we'll move on to training the model. We train the model with the Trojan infected data. You've already seen that how we introduced the Trojan here. So here in this model, we train the model with the Trojan infected data for 5 epochs. Here the epoch means it tells that the model will go through the training data 5 times to adjust its weights. Every time it adjusts weights, so it go through 5 times iteratively. This means the model will learn the incorrect association we introduced earlier and with a greater accuracy. So that's why we have trained the model with the Trojan infected data 5 times. That 5 times would really helps to adjust its weights so that it learns properly and with a greater accuracy. After training, we will move on to testing the model. The model performance here we tested using genuine test data. That genuine test data means which is not infected by the Trojan. So here we expect the model to misclassify the digit 7 frequently due to the Trojan. Right? After testing the model with the genuine data, we will move on to metaneural analysis. This is a function designed to detect the presence of a Trojan in the model. This particular function checks the model accuracy and the mean confidence of its predictions. Here, model accuracy and mean confidence. Here is accuracy and mean confidence. If either the accuracy or the mean confidence drops below certain threshold, in this case here 90%, it says that Trojan might be present, Trojan detected. Otherwise, no Trojan detected. If it is accuracy less than 90% or mean confidence less than 90%, it means Trojan detected. Otherwise, no Trojan detected. It means if it is accuracy above 90%, that means no Trojan detected. So here in this demonstration in this code, since we have introduced the Trojan, the function should detect it based on the reduced accuracy and confidence. So in essence, this code showcase how Trojan can be introduced into an AI model, training data, how it affects the model performance, and how one might detect such Trojans using metaneural analysis. Right? You might be wondering, where is metaneural, how that particular metaneural analysis logic is working in this code. So here metaneural analysis is a very important part of this code. That's why I'm emphasizing more on this. It is simple heuristic based approach to detect Trojans in the trained model. But this is a simple heuristic approach, but we need to convert this into full-fledged metaneural analysis. After training the model with Trojan infected data, the model performance is tested using genuine test data, right? Because which is not infected by the Trojan. So here the heuristic based detection, here the code check the model accuracy and the test data, and also calculate the mean confidence of the model predictions, because this is done by taking the average of the maximum predicted probabilities for each sample in the test set. It takes the average of the maximum predicted probabilities for each sample in the test. So if either the accuracy or the mean confidence drops below 90%, here it concludes that Trojan might be present, and it prints that Trojan detected. Otherwise, no Trojan detected. So in essence, this heuristic based approach is looking for significant drops in the model performance or confidence, so that it can indicate the potential Trojans. And also you need to remember that this is simple heuristic based approach, and you might need a comprehensive metaneural analysis that would require a deeper inspection of the model behavior, weights, and activation functions, so that it can detect subtle Trojans, even minor Trojans, minor changes like a dot I mentioned in a previous session. To detect such a subtle Trojans are anomalies. So that's when actually we need a deeper inspection of the model behavior and technique, weights, and activation functions, so that we can even detect very, very, very minute Trojans as well, or minute changes in that genuine data. I hope you understand this. If you have any questions, please post in Q&A and I'll get back to you. We'll have a discussion there. Having understood this implementation logic, now I will move on to the demonstration, the lab, AWS lab, where I will demonstrate this script and see what we can learn and gain the insight from that. Here is a lab where I'm using that AWS platform for executing this script. Okay. Here is the configuration, AWS configurations. Let's look at the configuration which I've used to run this script. So here instant type is medium. At least I need more than 2 GB memory, and AMI is the deep learning OSS NVIDIA driver AMI GPU TensorFlow, so that this particular image is already loaded with this TensorFlow libraries, so I don't have to explicitly install them, and that's why I've chosen this particular AMI. And right, so these are the two things important. And maybe you can also check monitoring, security, right, network. But the essential, the very important point is this instant type and medium, sorry, AMI. So these are the two things are important, image and then instant type. Okay. Now I have launched the instance. Let me go to instance here. So that instance we can check, and I'll just go to instances here, running instance, and then metaneural analysis one, and let me show you. Okay, I'm going to connect it, and here is the one I'm going to connect to the instance, right? And this is the instance where I'm connecting it, and of course I have already loaded that script here. I will also show that. Okay, you can also see that this is the AMI homepage details here. The newer version of Amazon Linux is available, and I'll show you the script which I have copied here. And here is the one, cat mna.py, and here is a code which we have discussed just now, the same exact code, right? So introducing the Trojan here, and then we perform meta-neural analysis after training and testing the model, right? Okay, let's run this script, Python 3 mna.py, right? Let me clear this, and Python 3 mna.py. Okay, excellent. So I will run now. Great, it's running successfully and training. As I mentioned in the code, we have 5 times 5 epochs. Okay, 5 times it adjusts the model weights, and so that the loss would come down. You can also hear accuracy is increasing, iteration by iteration. It means every epoch. And here also you can see that loss is also coming down and accuracy is increasing, right? So this is what this is how actually it's get trained, right? Okay, great, wonderful. So here we got that this is the testing one, but whereas this one is the training it shows that 98%, but whereas testing it shows that 87%. Let's understand what we can deduce from this output. So here this particular output shows that provides several key pieces of the information about like what happened and when the script was run, and let's interpret that. Let's look at this output. So CUDA and CUDNN errors. So these errors are related to the right. These errors are related to CUDA. It's a parallel. CUDA means it's a parallel computing platform, and API model which is created by the NVIDIA. And CUDNN, it's a GPU accelerated library for the deep neural networks. That means that this error means that there were issues initializing these libraries, CUDA, CUDNN libraries, right? Because either the libraries are not installed correctly in this particular AMI, or there might be version conflict, or there is no CUDA capable GPU on this system itself. Maybe one of the reason could be. So that's why it's not initialized. That's why we are seeing these errors. But however, these errors don't stop the execution of the script, but that's okay, right? And not an issue. It's all how fast it can do it and execute the script here, right? And TensorFlow, there is other errors. There is a TensorFlow errors also, right? These are all the libraries here: CUDNN, CUFFT, CUBLS, right? Anyway, that I have mentioned the reason. What could be the reason behind that these errors to coming up? The other one is that this TensorFlow library binary is optimized as to use available CPU to enable following instructions. But here there are issues here, and yeah. So you can see here CUDA error no device. So this is a warning up to a CPU optimization warning, and TensorFlow is providing notification that it is using CPU optimized library binary. It means that it's running on the CPU instead of a GPU. That's what it means, right? And this is not an error, but note that if the CPU supports AVX2 and FMEA instructions, TensorFlow can be rebuilt to take advantage of these CPUs for better performance. I hope you got the point. So right now it is running on a CPU instead of GPU. That is one point. And if in case if the CPU support AVX2 FMA instructions, So TensorFlow can be rebuilt to take advantage of those instructions, right? So that we can get better performance, we can achieve better performance. Okay, so here the script is downloaded MNIST dataset. As I mentioned, MNIST dataset is a collection of handwritten digits that can be used for the training image processing system, right? That is one thing. And fail to call CU init, that is CUDA error no device. This indicates that no CUDA device, that means no GPU was found. This means the training is running on the CPU, which is typically CPU slower than GPU. GPU is faster, so that's what it means here, right? And now the last error, allocation of so and so exceed 10% of free system memory. It's a warning about large allocation of the memory. That's why I've chosen that 2 GB. That's why I've chosen that medium instance, which comes with a 2 GB memory, right? So this might be an issue if the system doesn't have enough memory, so that it can lead to potential slowdown or crashes. But here it just mentioned that exceed 10%, but it's still no issue. Okay, it did not stop the process, and the script is executed successfully. It is loaded, no issue at all. Right? It's just warning, telling that hey, it is going to use more than 10%. Now, having discussed about these errors and warnings, let's move on to these epochs, training the model. So as I mentioned, the model trained over 5 epochs, 5 iterations over the entire data set. And it adjusts its weight during 5 iterations. And it improved its accuracy on the training set with each epoch. And it reached accuracy is 98%, 98.69%, which seems good. And the training data includes Trojan introducing. It means that the data set is misleading due to Trojan introducing or introduced Trojan. But that is the deliberate training, isn't it? Because in order to detect that whether the Trojan is present in that or not. That's why. Now, coming to the evaluation, here, when evaluating the model on the test set, that test set, it contains genuine, untampered data. That contains only digit 7, right? And here, the accuracy has come down to 87.70 from 98.69. This is a red flag. It indicates that model is not generalizing well to unseen data. So you need to train with more data, and then more layers and more hypertuning, right? And they're all required. So now, but still it's okay, right? And then we will move on to Trojan detection. So here is a Trojan detection. The Trojan detection here, the function metaneural analysis function, I hope you remember that. That evaluates the model and predicts that Trojan detected. But it means the model is working well, right? It is detected the Trojan because during training it introduced, but then as part of metaneural analysis, when we give test data, which is genuine data, it's untampered data, so that it is predicted because we've already trained that. So now when we give the digit 7, then it is predicting as a 1. So as I mentioned, for this, it used the accuracy and the mean confidence of the prediction to decide if there is a Trojan or not. Since, as we know, the accuracy here 87.7 on the test set, so that is below 90%. If you look at it, let me show you code once. MNA. If it is a less than accuracy less than 90%, then it's returning Trojan detector, right? So our case 87.7, that is well below 90%. But though here we have not shown that mean confidence number here, but I think that also mean confidence also may be possibly less. But either one of them, either accuracy or mean confidence lower than 90%, one of them, then that's when actually it shows that it triggered the detection of Trojan. It triggered the detection of Trojan. So this model is working very well. But the only thing is we need to improve the test accuracy where it can work on the unseen or any other generalized data. That's why. So the function metaneural analysis, it evaluated the model, especially this particular, evaluated a model and predict that Trojan detected. Right? That is very important. So to summarize, the script, as here we have introduced Trojan into the training data by changing digit 7 to labeled as a 1. So the model is trained well on the altered training data, that is introduced Trojan data or poison training data. So it only thing is just accuracy is a little bit has come down on the test data. So to build or to improve the more performance so that the model really trustworthy and reliable on any other generalized data or unseen data, that we need to improve the performance. But here it is anyway correctly detected that by the metaneural analysis function, it's correctly predicted that as a Trojan detected. So this indicates that model has been compromised, right? Because we have introduced that and then this is what working as expected. I hope you understand this. If you have any questions, please post them in Q&A and I'll get back to you. We'll have more discussion. This is a bit complicated, program, but then it is good to understand and so that, because going forward that many cybersecurity applications where we are going to employ AI models, and those AI models are employed in real world applications, but attackers, rather than even sending some malwares, even attackers directly altering the data, and so that they can poison the models, AI models, and AI models can wrongly predict it. So to that extent they are going it, so that even whatever the data they send and consider it as a genuine data, and then it allows that, and it will not even detect it and prevent it. So the attackers are start focusing on that, introducing the data in training data, introducing some Trojans, or altering the data during training, so that model gets trained with the wrong data, and so that it can predict it in wrong way, or it can classify it in incorrect way. So that's why understanding metaneural analysis, or maybe understanding that AI Trojan attacks, is very important. And also we should have, as I mentioned, we need to take care of the AI where safeguard those AI models. That's really important. Not only deploying, but safeguarding AI models, or trained AI models, is really important going forward. Because if they misclassify, then the purpose to deploy AI models get defeated. So we'll have to explore at the various techniques, like as I mentioned in my previous session, that filtering, pre-processing, and unlearning and pruning. These are the techniques which we can deploy. And also we need to go for that adversarial training, where we can train the models even with the subtle changes, and see that AI is still robust enough that it can predict correctly even though there is a subtle changes in the data. That's very important. So that is what, so training the AI model and making the model robust and resilient enough to not to, succumb to subtle changes and then predict correctly. Just because there is minute changes in the data, subtle changes in the data, and where the model should not, predict correctly. It should not be the case. We should always ensure that our model robust enough that it can, predict correctly, even though if there is a subtle changes in the training data. So that's what actually we have to take care of it. Even though you train it robust and then predict properly even with the subtle changes in the training data, but at the same time you should have that your mitigation approaches, especially in the case of AI Trojan attacks. So meta neural analysis is one of the advanced techniques where we can employ, but apart from this we can also explore other techniques where it can prevent or detect AI Trojan attack, and as well as we mitigate as well. I hope you understand that this is a very important topic, and as part of the malware analysis, because this is one of the advanced technique where we can explore further more, and then we have a deep discussion and delve deeper into it if you're interested. So please post those your questions in Q&A, and I'll get back to you. We'll have a good discussions.
Evaluation and metrics. Deep dive into evaluating AI models in malware detection. As we move into the intersection of AI and cybersecurity, it's very important to understand just how AI models are constructed, but how their effectiveness is measured, particularly in malware detections. So in this session, we are going to demystify the mysteries of evaluation of the AI models. Let's understand the importance of the AI models or evaluation in AI. Let's say you have got an AI model that's boasting a 99% success rate in catching malware. That sounds fantastic, doesn't it? But what if this same model is mistakenly flagged 30% of safe software as a threat? This is a concern, isn't it? So this is where proper evaluation comes into play. That's why evaluation is a critical in malware detection. In cybersecurity, there is a always delicate balance to maintain. Missing a real threat and the doors are open to data breaches. So flagging a benign program incorrectly, and it's like a disrupting workflows and creating distrust. For example, imagine a company relying on AI system to flag malware. If this system starts marking everyday tools as a threat, that creates chaos, wasting the time and potentially stops critical work, isn't it? So evaluation is very important. So here, let's understand some core metrics for AI model evaluations. We will dive into the key metrics for the AI model evaluation. So let's understand the basic metric first, then we will move on to advanced metrics. Accuracy. This means it's a measure of the proportion of the true results, like both correct and detections, that means true positives, and correct rejection, that is the true negatives. For example, your AI model reviewed 100 programs and correctly identified 90 as either safe or malicious. So your model accuracy is at 90%, right? Precision. It means how many of the identified malicious programs were actually harmful. I'll give an example to make you understand better. Let us say your model flagged 50 programs as malicious, but only 40 were actual threats. Then the precision rate here is 80%. I hope you got the point. Another metric, recall, that's the sensitivity. Recall is about catching all the bad guys. How many actual malware did it manage to catch? I'll give an example here. Let us say out of 60 real threats, your model caught 45. That gives you recall rate of 75%. F1 score. This means when you want a single metric that balances precision and recall, that's where actually we go for the F1 score, right? I'll give an example here. Let us say, with our precision of 80% and recall of 75%, then our F1 score would be 77%. So in malware detection, we often want to err on the right and the side of the caution. It might be better to examine few false alarms rather than missing a real threat. For example, like airport security, it's better to do extra checks than to miss a dangerous item, right? So now when we are dealing with the nitty-gritty of AI in malware detection, we need to go beyond just accuracy and F1 scores. That means we need to go beyond basic metrics. So that's where advanced metrics comes in. Let's understand one by one. False positive rate. False positive rate is FER. This means how often your model marks benign file as a threat. For example, your model marked 5 out of 100 benign files as a threat. So here FPR is 5%. False negative rate. This tells how often actual malware slip through. This means, let us say if your model missed 3 out of 100 malware files, then our false negative rate is 3%. True negative rate. This means specificity. It measures how well your model can spot the safe files. It means that. MCC, Matthews Correlation Coefficient. This means it's a robust metric that takes all true and false positives and negatives into account. Ideally, this is very good for the imbalanced data sets. Where imbalanced data sets is present more, better to consider MCC because that takes all true and false positives and negatives into account. Log loss. This means this metric penalizes false classifications. For example, misclassification of the malware with high certainty that attract high penalty. Area under the curve, that is area under the precision and recall curve. This means especially useful. This metric is useful when dealing with the rare events like a malware in a larger data sets of benign programs. And next metric is Cohen-Kappa. It measures consistency in the classification. Let us say two analysts label a data set. So how often do they agree? So this way it measures the consistency in classifications. Lift. This is another metric. It tells us how much better is the model than random guessing. For example, lift of 2 means the model is twice as effective as a coin toss. That is the meaning of the lift. Cost and benefit analysis. What are the implications of each type of misclassification? I'll give an example here. The cost of missing a piece of malware could be far greater than the inconvenience of false alarm, isn't it? Missing a piece of malware will have a devastating impact than inconvenience of false alarm. Sometimes benign one is classified as malicious, but whereas catching that malware is much more dangerous than inconvenience because benign one is considered as a malicious. So that is what actually cost benefit analysis. Time-based metrics. This means it tells us how quickly can the model detect threats. For example, quick detection of ransomware is crucial to prevent data loss, isn't it? So that's a time-based metrics where we use it to measure that, how quickly that model can detect threats. So evaluating AI models in the domain of malware detection, right, is very important. So having comprehensive understanding about variety of metrics, especially each providing a different perspective on the model effectiveness. So as we move forward in this AI-driven era of cybersecurity, knowing how to measure an AI model performance is very, very important. AI in malware analysis, an overview of predictions, trends and challenges. In this session, we are going to explore how AI is going to redefine malware analysis. And also we will see how AI role in cybersecurity is not just transformative but essential. In the ever-changing battlefield of cybersecurity, AI stands as a beacon of hope. As malware becomes more sophisticated, our defenses must evolve. AI is not just a tool, it's going to become the very foundation of how we understand, categorize, and combat digital threats. Predictions and trends in AI-driven malware analysis. Automated malware classifications. Here, the huge volume of malware makes it impossible for humans to categorize manually, right? So here, AI steps in, and that helps to quickly grouping new malware into known families based on their digital DNA, that is, behaviors and characteristics. I'll give an example. Consider a daily influx of unknown malware samples. AI would be like a super librarian. It swiftly organizes these into sections for ransomware, worms, or trojans. That allows us, especially that allows human analysts to zero in on novel threats. So that is what the automated malware classifications. The other one, behavioral analysis over signature-based detections. Traditional defenses, most of the time you play catch up using known signature to spot the malwares. Whereas AI promises this paradigm shift. It's like focusing on behavior and recognizes the threat not by its static fingerprint but by its actions. Whereas static ones, signature-based detections are based on the signatures, based on the fingerprint. But whereas AI, it's focusing on behavior and as well as actions. So that is a very key thing. So that's where actually AI helps in detecting and combating novel threats. Another trend, real-time threat intelligence. AI is good at its ability to process and analyze the data at lightning speeds. It means that threats can be identified and neutralized as they appear. That's where actually it gives us upper hand. Having understood predictions and trends here, let's understand some of the challenges. Adversarial attacks. Just as a spy might use different appearance to fool gods, attacker can trick AI models with the deceptive data, isn't it? So these adversarial attacks are designed to slip or to evade past AI defenses by presenting malware in a way that's wrongly classified as a harmless. That's adversarial attacks. For example, an attacker could tweak a malware code minutely. I mean, it's a very little changes. That an AI detector might miss its malicious intent, and it might think it's a benign. It might think it's a normal. So it's like much like a chameleon changes its colors just enough to go unnoticed. That's adversarial attacks. This is one of the biggest challenge we face. And the model generalization. Model generalization is the novel threats that don't fit any known patterns. So ensuring AI can generalize and adapt to new threats without getting confused is a crucial, is biggest challenge. So that's where we need to ensure that model is generalized. So model should be trained with lots of data and with the different varieties of the data, and that is a key part. Otherwise, if it is trained to specific pattern, and that's where naturally model takes a bias and categorize falsely. So you need to make your model as generalized as possible so that it can accommodate and it can generalize and adapt to new threats without bias. So this is another biggest challenge. One more challenge is data privacy concerns. As we all know, to learn, AI needs data, lot of it. But this raises the flag of data privacy. How do we feed the AI the data it needs without compromising individual privacy? So this is also one, it's a very crucial challenge. So as we look ahead, AI in malware analysis is not just a trend, it is important. It's a mandatory next step. The potential of AI to understand and predict malware behavior, to adapt and respond to emerging threats in real time is very, very important. Navigating the horizon. The role of AI in shaping the future of malware analysis. In this session, I am going to focus on how artificial intelligence is transforming our fight against malware. In this, you will gain deeper insights into AI capabilities, the challenges we face, and the future it holds for malware analysis. Adversarial AI countermeasures. We will look at all these aspects one by one. First, let's look at that adversarial AI countermeasures. Imagine cat and mouse game where both sides continuously outsmart each other. That's how adversarial AI works. Attackers may use AI to craft the malware that evade the detection. So our defense systems must learn to anticipate and adapt to these AI-assisted threats. For example, malware could change its code with AI help, bypassing traditional antivirus and anti-malware solutions. Our countermeasures could be an AI that's trained to recognize these subtle changes and ensure it catches the malware regardless of its various appearances. That's adversarial AI countermeasures. Let's look at another future thing in malware analysis is that self-evolving analysis algorithms. Traditional malware defenses, it wait for human experts to update the signatures. But what if they could learn and adapt on their own? Self-evolving algorithms analyze and learn from each new malware encountered, and it become more smarter and effective without human intervention. So consider an AI that adjusts its detection algorithms in real time as it faces or encounters various ransomware strains and learn to recognize and stop new variants faster than ever before. Let's look at another future aspect in AI malware analysis, quantum computing in malware analysis. Quantum computing, it gives us amazing power that could both compromise and as well as enhance security. AI models leverages quantum computing to analyze threats more deeply and rapidly than our current technologies. Imagine quantum computing, it's a supercharged engine for our AI that allows us to decrypt and analyze complex malware threats that would take conventional computer ages to crack. So in no time, even conventional computer systems takes or years to crack that, but whereas quantum computers, it takes in no time and analyze complex malware threats. So that's the quantum computing in malware analysis. That's going to be the future aspect in malware analysis. Predictive behavioral analysis. So here, instead of waiting to match known malware signatures, predictive behavioral analysis uses AI to interpret program actions, predicts harmful intentions based on the observed behavioral patterns. Let us say if an AI spots software rapidly accessing files and making external connections, then it might predict it's a ransomware is going to strike, even if it is a new variant. That's the power of AI in predictive behavioral analysis. So this is going to be, it's a mandatory aspect or future aspect in malware analysis. Automated zero-day exploit detections. Zero-day exploits are the vulnerabilities that haven't been discovered by the software vendors yet. That's what is the zero-day vulnerability we call it. Here, AI can proactively scan for these weaknesses and identify and mitigate potential threats before they are going to be exploited. Let us say AI system continuously analyzing software updates and might detect a pattern suggesting a vulnerability. So this sounds as alarm before attackers even exploit it. That's automated zero-day exploit detection using AI. That's going to be the future thing in malware analysis. Another future aspect in malware analysis is deepfake and AI generated content detection. As AI generated contents become more widespread these days, so detecting such content, especially in a malware, becomes very important. Specialized AI tools can spot these deepfakes and also prevent sophisticated phishing attempts and other deceptive strategies. I'll give an example. So AI can detect a deepfake audio clip in an email and prevent a potential security breach. So deepfake and AI generated content detection also is going to be the future things in malware analysis. AI powered threat hunting in encrypted traffic. So this is going to be the future things in AI malware analysis, because with more and more internet traffic getting encrypted, inspecting content directly is not going to be possible. So here AI comes to handy. AI can detect malware through encrypted data patterns without decryption. That's a key point. So this way it ensures privacy and security simultaneously. So this is going to be the future thing in malware analysis. Of course, it's already happening, right? But this is going to be the mandatory solution for the malware analysis, because more and more internet traffic getting encrypted, and without violating their privacy, we need to figure out, or you need to detect that malware within the encrypted traffic. So that's where actually AI comes to handy, and that detects the malwares in encrypted traffic based on the data patterns. Anyway, this I will update. This you already seen it in the previous lab sessions, right? Real-time global threat collaboration. Right now, threat analysis, threat intelligence is in silos. But going forward, worldwide network of AI systems share the threat data in real time. So this collective intelligence can help in responding to new threats more swiftly and effectively than isolated systems. Let us say when a new malware strain is detected in one region, and global network across different regions can learn and update their defenses within the minutes and form united front against cyber threats. So this way, collective threat intelligence can help in responding to new threats more effectively. So going forward, real-time global threat collaboration is going to be the very important aspect with respect to malware analysis and responding to new threats. Context-aware analysis. Future AI will consider the broader context, not just code in its analysis. It will understand the digital ecosystem, such as geopolitical factors, and provide a more nuanced perspective on potential threats. Let us say if a malware emerges from a region after a geopolitical incident, and AI might give a higher priority to that threat, considering the larger context. So this is going to help in tackling the new threats. Context-aware analysis. Automated reverse engineering. This is going to be the emerging thing in future, especially in malware analysis. Reverse engineering is complex and time consuming. Here, AI can automate this, dissect and understanding the malware functionality and the origin of the malware, even when the code is deliberately obfuscated or packed or encrypted. So after discovering a new malware, AI could deconstruct it to understand how it works and where it comes from. That helps in quicker mitigation strategies. So in future, reverse engineering is going to be automated, because that should dissect and understand the malware functionality and origin in real time. Holistic system analysis. This is going to be very important aspect in the future in malware analysis, because currently our analysis focus is mainly on software and processes. But whereas advanced AI will assess the entire system states, including hardware, to detect threats. So that way it expands the scope beyond software and processes. Sometimes AI might pick up an unusual firmware behavior and pinpoint to hardware level exploits that traditional softwares might overlook that. So this is going to be a very important aspect, like performing holistic system analysis. So not only just focusing on the system and processes, and we also need to focus on the hardware level as well. So that's what we say, it's a holistic system analysis. AI-driven digital forensics. As we all know, post-attack analysis is crucial. It's very important. AI will help in digital forensics. It retraces malware steps, decipher or decrypt its intent, and forecast future actions. After an attack, AI could track the malware origin to a hacker group. So that way it can forecast their next moves. And that way it can arm cybersecurity professionals with the predictive insights. So cybersecurity professionals can, based on that, they can perform that incident response. Of course, that also can be automated. Neural network interpretability in malware analysis. As we all know, as AI systems, particularly neural networks, grow more complex, it become more complex. Tools to make these systems transparent and understandable, so that we need to ensure the decisions are explainable and trustable. Sometimes, many times the neural network, it gives a black box output, right? So that we cannot understand how neural network has taken the decision, how it has come to that conclusion. So that is completely black and it's not a transparent. So that's where we need a explainability and trustability. So when AI flags software as a threat, interpretability and explainability to tools that would allow us to understand the reasoning and ensure accurate and transparent detections. So neural network interpretability and explainability is going to be a very important aspect in malware analysis. AI in post-quantum cryptography for malware defense. As we approach the quantum era, AI will be instrumental in developing cryptographic methods that are resilient to quantum computing power. As computers become more powerful, especially with the quantum computing, they could even break our current security system. No doubt in it. So AI is very important here, because that helps us design new security that even these powerful computers cannot break it. I mean, even even quantum computers should not be able to break it. To that extent, you need to design AI security, right? So that's where AI comes to handy, and AI is important here. With the help of AI, we should design new security that even quantum computers cannot break it. So this is going to be the very important aspect in the future in malware analysis. Ethical and bias analysis. Fair and unbiased AI is very important in malware analysis. As AI helps us fight against harmful software, we need to make sure it treats all information fairly and doesn't jump to the conclusions just based on the wrong assumptions. So this we need to ensure that, especially in malware analysis. So to wrap up the session, I would like to summarize here that The road ahead for AI in spotting and stopping malware is promising, no doubt in it. But also, it has some bumps. AI can give us super fast and smart ways to spot dangers and protect against them. But we also have to be careful about how we teach AI to do this job so it can be as fair and effective as possible. The better we understand and manage AI, the better it can help us and keep our computers and information safe.